My name is Rob McQueenie, and I'm a director of what's called CATS, which is the Center for the Advancement of Topological Semimetals. And so this is BES Energy Frontier Research Center, which has been funded since 2018. And the mission of the center is to discover, understand, and harness new topological states of matter. And one of our focus areas is on correlated topological states of matter. This includes things like kagome metals, twisted bilayers, other moire systems, sort of quantum limit and high magnetic fields, and so forth. And so we've been very interested in these 166 kagome metals, and sort of we just generally organized topical workshops within the center. And we thought this was one that was of a lot of interest to everybody across the center. And so we worked on these materials a little bit, mainly neutron diffraction, inelastic neutron scattering, thin film growth, high field studies very recently. And so you'll hear about some of those results today. But as I said, you know, we periodically host these workshops. And so, you know, one thing that we like to do is to kind of share with the community and discuss these kind of areas of interest to the center. And so, you know, what we'd like to accomplish in this workshop is to, you know, discuss some of the forefront issues in these materials, identify some of the open questions that arise across this set of materials, and identify areas for collaboration. I mean, we are a center, we're interested in working together, but we also have a mandate to collaborate externally with other people. And so, regards to the agenda, so I'm not going to go through this in detail, but Anand will chair the first session, and we'll have session chairs for each of these sort of blocks. And so, as Anand had just said, the talks are scheduled for 20 minutes, leaving a lot of time for questions at the end. So 10 minutes for questions at the end. And then over lunch and at the end, there'll be time available for just open discussion about all the talks. And so the one change in the agenda was Zahid. I had only given him 15 minutes at the end, but of course he should get the full half hour. And so the end time of the workshop has changed 15 minutes. So just one thing about these virtual workshops, just a few rules for the road. Edit your name on Zoom so it shows your full name. So if you're asking questions and things, that people can call you out by name. Of course, mute your microphone unless you're speaking. Try to speak one at a time. And you can ask questions, and the chair will acknowledge your questions by either raising your hand in this Zoom function, or you can just type the question into the workshop chat, and the chair will go through and call those questions out. Again, there's plenty of time for questions, so I think it's somehow tricky to interrupt the speaker and ask questions during the talk. So please wait till the talk is over, if you can sit on your hands till then, and then there'll be time at the end to ask questions to the speaker. So just one more thing, I want to thank Anand, and I want to thank Joe Chkelsky for co-organizing the workshop. I want to thank Corey for setting up all the logistics on the workshop. We plan on recording the workshop. You got that notice there. We post these workshops on the CATS YouTube channel. You can go there and see other workshops if you want, but you can opt out. So if you don't want your talk to be shared in this format, just let me know or let Corey know, and then when we go through and put the video together, we can scrub it. Anyway, it looks like a great agenda. I'm really excited to learn more about these materials. And so at this point, I'll turn it over to Anand. I'm going to stop sharing here, or I can put up the agenda for this session here. So Shuang will be first, but I'll turn it over to Anand. Any questions for me before that? Perfect. All right, Anand.
Yeah, thanks, Rob. I think should we wait till 8:30, Rob, because that's
I would.
Time.
Yeah.
So I'll just give everybody a short 3-minute break here, and we'll come back at 8:30. Our first speaker today is Shuang Jia from Peking University, and so welcome to this meeting, everybody, and the first session. And my name is Anand Bhattacharya. I'm from Argonne National Laboratory. And Sean will be telling us about anomalous transverse transport in kagome magnet RM6X6. Sean, take it away.
Okay, thank you. So at first, I want to thank the organizer of this online workshop, Professor Rob McQueen. As you know, I graduated from Iowa State University in 2008, and Professor Paul Canfield and Rob are my advisors. So I would like to thank Paul as well. He's one of the first researcher to synthesize a single crystal 166 compound from tin flax, and he also studies the magnetic anisotropic properties in 1990s. I think his work inspired our research. Okay, this is the outline of my talk. Firstly, I introduce some basic knowledge of anomalous transport effect. Then I will talk about the anomalous Hall effect and anomalous Nancy effect and the summer Hall effect for RM6X6, including the anomalous Hall effect for the chain gap kagome magnet turbine 166. And then I talk about the charge entropy scaling of the turbine 166. And then the anomalous Hall effect for other rare earths 166. Okay, so this slide is about some introduction of anomalous Hall effect. So before the anomalous Hall effect, you know the ordinary Hall effect, which was discovered by Edwin Hall in 1877. So if you apply a magnetic field perpendicular to the current, you will have some charge accumulated on the two sides of the sample, and that give you electric field, which cancels the Lorentz force. So we have a Hall resistance, which equals Hall voltage divided by the current, equals B divided by Q, which is charge. N is carrier density, D is thickness of sample. So basically, we have a Hall resistance, which is linear dependent on the external magnetic field. Of course, it's a single band model. So after 2 years, he also discovers the anomalous Hall effect on a piece of iron metal. So you can imagine the iron has a spontaneous magnetization. So this M may somehow replace the work for the external magnetic field. However, if you measure the anomalous Hall effect for the piece of iron or iron thin film at different temperature, you see this anomalous Hall resistance is not dependent on the carrier density. So, so why and how the magnetization plays a role on the anomalous Hall effect, that need almost 100 years to understand it. So currently we understand the mechanism of the anomalous Hall effect due to 3 different mechanisms. One is intrinsic, in which the electrons have an anomalous velocity perpendicular to the electric field, which is due to their Barry curvature field. And because at that time, the anomalous velocity is independent with the electron's lifetime, so you have a anomalous Hall conductivity equals a constant. The other 2 mechanism is extrinsic, including side jump and skew scattering. For the intrinsic anomalous Hall effect, we understand it as a Barry curvature field effect, which is similar as a geometric phase. So this is a pendulum on Earth. So after 24 hours, you notice this direction of a pendulum will rotate one angle, which we call the geometric phase angle. So that's the reason we can use that to describe the topological property of a sphere when it's a rotation. For electrons, you will see a similar behavior. So if you have parameter operator, you have parameter space Q, which is have a closed circle around C, and the electron wave function will acquire additional Barry phase angle. And we assume there's an effective magnetic field on the K space, which will produce this Barry phase angle. So this effective magnetic field will act on the electrons moving, give it an anomalous velocity. That's the reason we have an intrinsic anomalous Hall resistance on conductivity. So basically, we can use a first principle band structure calculation to calculate the Barry curvature field, and then we obtain the anomalous Hall conductivity and use that to compare with experimental result. Besides anomalous Hall effect, we also have a anomalous density effect, which describes a temperature gradient generate a transversal voltage, and we have an anomalous Sommerhall effect. Although the other two effects are less considered in the current experiment. So currently, people pay more attention on the anomalous density effect because it has some potential to be energy conservation devices. So for Seebeck effect, you need N-type and P-type devices to form a matrix, and you change the temperature gradient to a voltage. Because anomalous density effect is transversal effect. So basically, it is easy to design some devices to do this energy conservation. However, because the anomalous density effect had relatively less small coefficient compared with Seebeck coefficient, it is urgent to discover some new material with a giant anomalous density effect. We also have a quantum effect counterpart for the Hall effect and anomalous Hall effect, which means quantum Hall effect and quantum anomalous Hall effect. For quantum Hall effect, at this state, you have a chiral H state, which can be described as a quantum number n, and you have an insulating state inside of the sample. For quantum anomalous Hall effect, without an external magnetic field, you also have this quantum number of resistivity. At this point, Professor Xue Qikun using some magnetic irons doping inside the topological insulator that will give effect mass to the massless diaphragm. That opened a Chen gap on the surface state and generated Chen equals 1 Chen gap state. And if the energy is inside the gap state, you observe a quantum anomalous Hall effect. So our motivation for exploring kagome magnet is from the Houdin model. In the last slides, we described that quantum anomalous Hall effect can be achieved by breaking time reverse symmetry on the surface of a topology insulator. Actually, the first proposal coming from Professor Houdin, he suggests a honeycomb lattice with a staggered magnetic flux can generate a quantum anomalous Hall effect. So on the other hand, if you consider a two-dimensional honeycomb lattice, including the spin orbital coupling and time reversal symmetry breaking, and the Kim-Mill model suggests that you will also have a Chen gap opening on the K point. And if the energy is on this point, you see a top quantum anomalous Hall effect as well. Because honeycomb lattice is relatively rare in solid, we consider its line graph lattice, kagome lattice. Kagome lattice is a highly frustrated lattice, which have potential to bury in some exotic state like quantum spin liquid. On the other hand, if you use a tight banding model to calculate the band structure, you find it has 3 bands. One is a flat band, other 2 bands just like what inside the honeycomb lattice, which has a band crossing point at the key point. So if you including the SOC and time reverse symmetry breaking out-of-plane ferromagnets, then you will open a gap on this touching point. Also, you achieve a Chen number equals 1's kagome quantum magnet. Actually, in 2015, Professor Zhang Chouchen have predicted some materials like this one. So if you have autoplane fermions and SOC, you open a small gap on this band crossing point. So motivated by those theoretical models, people already try to explore some topological kagome magnet based on transition metal based kagome lattice. The old paper is from George Tchaikovsky. He discovered iron 3 tin 2, which has a double layer kagome lattice, and it is an in-plane ferromagnetic material. The ground state is a little bit complicated. Maybe it's a spin glass or something at a very low temperature. Magnets 3 tin, iron tin is also have a kagome lattice, but they are antiferromagnetic. The first magnetic wild sand metal cobalt 3 tin 2 sulfur 2. It is also have a cobalt-based kagome lattice, but it has a strong interplay coupling. So the band structure transfer from 2-dimensional lag to 3-dimensional lag. So you have some well point instead of a massive diaphragm, 2-dimensional lag. So based on those theoretical model, how can we design a chain kagome magnet? Basically, we need outer plane ferromagnetism. We need pristine kagome lattice. We also need a weak interlayer coupling. But the difficulty for the transition metal-based kagome lattice is that usually the transition metal has a small magnetic anisotropy, and there's no pristine kagome lattice in other kagome magnet. And also the interlayer coupling is really strong. So that makes the sample becomes a well-set metal. So our solution is try to measure the other structure, 166 cross structure. That equals you adding 5 local moment band rare earths in the cobalt-tin type structure. So this plot suggests how we introduce guessed rare earth atoms in the vacancy of the cobalt-tin atoms, and that rare earth will push the tin atoms up and down, give you a double space of a C-axis, give you a very large group of 166 compound. That is a very large family of iso structure and have various magnetic properties dependent on the rare earth atoms and the transition atoms. So before I discuss some transport properties, let's examine the magnetization for rare earths manganese 6 tin 6 at first. Basically, the magnetic structure is determined by the strong coupling between the rare earths and the manganese. Here, the magnetic coupling is indirect with the exchange interaction with the 5D electrons. So basically, the spin part of the rare earth atoms is anti-parallel with the position of the direction of a 3D local moment on the manganese. So if you have a light rare earth, meaning your Hounslow ground state L minus S, it is ferromagnetic. Well, if it's a heavy rare earth, it's anti-ferro. Sorry, it's a ferrimagnetic, meaning the 5 moment and manganese moment is anti-parallel. Fortunately, because 5 local moment have very strong anisotropy, so if you check the different rare earth elements, you find one element, which is terbium, have a very strong outer plane ferromagnetism due to a strong anisotropy of the terbium. And that terbium moment just polarized the manganese moment, make you achieve a ferromagnetic kagome lattice outer plane. So that's the reason we choose the terbium 166 as the first example to measure. This is a magnetization and anomalous Hall properties for terbium 166. It has an easy axis ferromagnetic state, which is very stable from 300 down to 2 Kelvin. And the saturation moment equals 6 manganese minus 1 terbium. And it's a hard ferromagnet. And it's also a large spontaneous anomalous Hall effect, which well follows magnetization curve. Also, even at 2 Kelvin, you see a very clear hysteresis loop in the Hall resistivity, indicating detectable anomalous Hall effect down to 2 Kelvin. So our collaborators, Professor Zaki Hassan in Princeton, his group doing some STM spectral measurement on the surface of terbium 166. They doing DIDV measurement on the manganese surface, the kagome surface, and also the terbium tin surface. Basically, they detect a very clear massive diaphragmian Landau fan diagram on the kagome lattice. And this fan diagram can be well described theoretical model which describe massive diaphragmian with a chain gap equals 34 millieV and the Fermi energy equals 130 millieV. After by induced bias voltage, so around 130 millieV, the Fermi energy were inside the gap. So they also detected a chiral age state in the STM spectra. So this is consistent with the theoretical prediction. So besides this spectral measurement, we can also detect massive diaphragm from the transport measurement. This plot is a scaling relation of a Knobs Hall resistance with longitudinal resistance. You see a very clear intrinsic Knobs Hall effect, and the Knobs Hall conductivity equals 0.14 quantum number per kagome layers. This is exactly same as calculated barrier curvature for a chain gapped diaphragm. Also, we can do some electron doping on this compound, and you see a strongly enhanced intrinsic Knobs Hall conductivity, which is consistent with theoretical model as well. We also detected a very strong quantum oscillations in turbine 166, even it is inside a Fermat state. So the quantum oscillation persists up to 30 Kelvin, and you see the effective electron mass is 0.14. Everything is consistent with band structure calculation and STM measurement. So this result indicating that we have very robust ferromagnetic ground state from 2 Kelvin to 300 Kelvin, and the massive diaphragm almost unchanged at this finite temperature. That indicating we can do some measurement on the thermoelectric and announced thermal conductivity measurement. And this plot shows 3 different announced effects in 166. And actually, we observe a strong announced length effect and also thermal Hall effect. So announced length effect is pretty large as 1.6 mu vol per Kelvin at room temperature. And this is comparable with other topological magnet. Okay, so how to understand this announced transport coefficient? Before understand this announced coefficient, let's check the longitudinal charge and entropy scaling. So usually we have multi relation with described relationship between the alpha, which is thermoelectric conductivity, to the electrical conductivity. And we also have Wiedemann Franz law describes a linear relation between the kappa, which is thermal conductivity, to the electrical conductivity. That is because we do some approximation on the Boltzmann equation. So think about electron moving on the electric field and temperature gradient. So the electron can both carry a charge and heat. So what is difference for the electrons inside the temperature gradient and the electric field? Basically, the Fermi distribution function in the electric field, you just shifted this distribution function to a small energy. Or for temperature gradient, you just change the shape on the Fermi surface. So that's the reason if you calculate the thermal conductivity and the electrical conductivity, you need to consider a transport distribution function times the derivative of Fermi distribution function to the energy for the conductivity. Or for alpha, you need times Fermi distribution to the temperature, which equals Fermi distribution function to the energy times KBT over 1. So this is a large difference. And at the low temperature, you will see the motor relation and the Wiedemann Franz law. So for the Knobs effect, basically the formula is similar. The only difference is that we replace the sum of barrier curvature field of the whole brane zone to the transport distribution function. So we times the derivative of Fermi distribution function and this sigma xy, we have a final temperature Knobs Hall coefficient, including the Knobs Hall effect, Knobs density effect, and also thermal Hall effect. So at this plot, I plot the pounding function at 100 Kelvin and 300 Kelvin for these 2 different Knobs effect. I also plot the barrier curvature distribution for the massive diaphragm. So think about if you have a very strong distribution of a gravitational field at a high energy state, the product of the Poynting function and the Barry-Culture function will be significantly different at a high temperature than to the low temperature. So that's the reason we detect a derivative from the Wiedemann-Franz law for the announced thermal Hall effect to the announced electrical effect. So besides this measurement on turbine 166, we also doing some measurement on other rare earths. As I said before, the rare earths and magnetism magnetic coupling determine the magnetic structure. So interesting, if your rare earths are changing from galenium to holmium to erbium, finally this compound becomes antiferromagnetic at zero temperature. So the very special thing is the erbium 166. So if you apply magnetic field, the compound will become spin polarized. At the same time, you see a clear Nernst Hall effect in this compound. So we compare all the intrinsic Nernst Hall conductivity for this rare earth atoms, 166 compounds, and we'll also detect a quantum oscillation for the samples. Using this parameter, we're using a massive DR fermion model. We can estimate the chain gap and estimate the Fermi energy for the massive DR fermion. We found an interesting scaling law. So the x-axis is the digest factor of the rare earth, and the y-axis is the gap size and the Fermi energy. We see the delta is dependent on the digest factor, while the Fermi energy of massive DR fermions depend on the square root of a digest factor. So this is a very interesting observation. Clearly, we cannot explain it by the Kim-Mill model because Kim-Mill model only explains the nearest neighbor hopping between the atoms. Yes.
Sorry to interrupt, Shang, but we're at the end of 20 minutes, so you may want to just keep that in mind. We have about 10 minutes for questions now. So.
Oh, okay. I'm finishing in 1 minute. So. Sure. So it cannot be explained by the Kim-Mill model, but if you consider some perturbation from the rare earth atom, it means you consider the hopping from manganese to rare earth and back to manganese, you can explain this interesting scaling relation. So this is our collaborator from PQ try to do in this explanation. We also measure the light rares. Basically, it's a ferromagnetic, but the Nernst Hall effect is same as a ferromagnetic. That indicating the Nernst Hall effect basically comes from the manganese atoms, not from rare earth atoms. So this is a work for the non-magnetic. We notice it also has a very strong topological Hall effect in E-train 166, but that's another interesting story. So I'll finish my talk. I would like to thank my collaborators, the STM RPS management Professor Zahid Hassan from Princeton, and thanks Wei Xie. She did some X-ray, single crystal X-ray diffraction measurement, and thanks our students. Okay, thank you very much.
Right. Sure. All right. Thank you, Anand. Thank you, Rob and Joe, for organizing this amazing workshop, and also thank you for the invitation. Today, I'll talk about these fluctuation-driven phenomena in kagome magnets, these rare earth magnetic 10-6 compounds. So this is getting tricky here. I don't know how to get rid of that, but whatever that is kind of obscured there was my outline and summary. I put them together just to make things clear that what I'll be talking about in this talk is about spin fluctuations. And spin fluctuations, we found that is very important on these R166 compounds. The first thing that we'll talk about is on the topological Hall effect in yttrium magnetic 10-6. The topological Hall effect, what we have found, it originates from spin fluctuation or thermal fluctuation causing the spins to fluctuate. And in terbium magnetic 10-6, that has an interesting spin reorientation transition, that these fluctuations also play a role in driving that spin reorientation. And also, this is something that is not available in the current theoretical understanding of the anomalous Hall effect, and I think we have made this empirically, maybe some observations that spin fluctuations may have contribution in the anomalous Hall conductivity also, and that's something that I wanted to bring up in this forum, the results, and I will be presenting some of the results about that. First of all, the yttrium magnesium 6 and here is the, let me do the pointer option, laser pointer, and here is this structure of yttrium magnesium 6. I think in this forum we all are very familiar about it. But the only thing that I wanted to mention is that how these manganese layers are stacked along the C-axis plays an important role on the magnetic structure of these materials, especially because if we look at between layer 2 and layer 1, it only contains the tin, and then when we look between layer 2 and layer 3, there's a rare earth and the tin containing layer. And because of that, the exchange interaction between layer 1 and 2 is different from the exchange interaction between layer 2 and 3. And if we include the nearest neighbor exchange interaction J3, then there is an inbuilt frustration along the C-axis, and that drives a lot of different magnetic phenomena in this material. And especially because the intralayer exchange is very strongly ferromagnetic, so it's mostly driven by the interlayer exchange interactions. And there are these single site anisotropy, Ising exchange, and if we apply magnetic field, we can tune these different interactions and drive different magnetic structure on these 1,6,6 compounds. And of course, due to all this complexity in yttrium magnesium 6, we can see even in the ground state, there are, interesting magnetic structures showing up. It orders with collinear antiferromagnetic structures just like that, as we can see here in the neutron data. And then as we cool down, then J3 becomes important. Then it twists this spin, and then it give rise to this spiral state, which we call this staggered spiral state. Now, when we apply magnetic field within the plane, we can tune all these different interactions and drive a lot of different magnetic phases. We can see like these 4 main magnetic phases here in the phase diagram. For field in plane. What these different magnetic phases are, that the first one is it starts with the spiral state, and you apply magnetic field in the plane, the spins start tilting in the direction of the magnetic field, and this makes this distorted spiral state. When magnetic field increases above this H1 magnetic field, then what happens is that you're applying magnetic field in the plane, but the spins you find it easier to move out of plane. It's pretty interesting. But they tilt along the direction of the magnetic field, and what that does is it forms these spiral states. It's called transverse conical spiral state. And then you further increase the magnetic field. These spins now find easier to now flop back into the plane. When they flop back into the plane here, they now this is a planar state, and it's not a spiral state. It has a 2q vector, as you can see here in this cartoon picture that I wrote at it. That I noted here is that this is one q vector and this is another q vector, and we understand very nicely why this happens. I'm not going into the details of this thing, and then it goes into the forced ferromagnetic state. So there are a lot of competing magnetic phases that can be tuned with external magnetic field. And one of the highlights in this material was this observation of the topological Hall effect that is coming especially at the higher temperatures, and you don't see them at lower temperatures. And at one particular temperature, if you look at into 245 Kelvin, for example, you have this nice peaked topological Hall effect within certain magnetic field. Now the question is, where does this topological Hall effect comes from, right? We know that for a topological Hall effect, we need a scalar spin chirality. And if we look at into this magnetic state, this transverse conical spiral state, where the topological Hall effect appears, this phase is at lower temperature also. This phase extends all the way up to a room temperature. But only at certain interval of this temperature, we see these the topological Hall is that certainly transverse conical spiral itself cannot generate the topological Hall effect because it doesn't have this scalar spin chirality. What happens in a very, I'll tell here in a very hand-waving way, is that what plays an important role is this 2-dimensional order of these magnetic atoms. It enhances these fluctuations, Marmin-Warren fluctuations. And because of these strong fluctuations, what happens is that This is a centrosymmetric material. We have equal, nearly equal population of the right-handed and left-handed spirals. And the fluctuation imbalances that population of the spirals in a very cartoonish way. Kind of try to visualize it, and that generates this third vector component, and then it comes the scalar spin chirality, and that gives rise to the topological Hall. Igor, who is here in the audience, developed a small theoretical model to this. And then, the calculated topological Hall matches pretty well with the measured topological Hall. And that's why we really believe that this is coming from the fluctuation-driven phenomena. So that's a fluctuation-driven phenomena on the topological Hall effect in yttrium manganese 6. Now, next, I will switch gear and talk about the terbium manganese 6 compound. And in terbium, now we have, instead of yttrium here, which was a nice system because the magnetism was coming only from manganese, we have terbium, and it complicates the exchange interactions. And this complication now brings about very nice, feature in the magnetization of this material, that there is a spin reorientation as at high temperature, as in the yttrium manganese 6. Both the terbium and manganese moment order in the plane. And when you lower the temperature, they move out of plane. And that generates this spin reorientation transition about 310 Kelvin. And we now think, in a very, simple mean field model, I think we can understand what is causing this spin reorientation. And again, this very quickly, I will explain this, that if we look into the Weiss field on the manganese atoms and terbium atoms, the Weiss field on manganese atom is pretty large as compared to the Weiss field on the terbium atom. Because of this, terbium atom fluctuates more. This is shown here in the cartoon picture as compared to the manganese atoms. And at lower temperature, the manganese atoms are not fluctuating as much as the terbium atoms. But as you increase the temperature, this terbium atom fluctuates much more than the manganese atoms. And it is consistent with the experimental observation also, the fact that there was, interestingly, this neutron experiment done way back in 1991, and they reported the magnetic moment on both manganese and terbium atoms. And we just replotted it here. So if we look into this moment of the manganese atoms, it remains pretty much constant over the wide range of temperature, and it decreases slightly at high temperature. Whereas the moment on terbium, sharply decreases. And that is one thing to think about, that it is the terbium moments are losing moment by the fluctuations, right? That's the case. Now, we also calculated the magnetic anisotropy energy based on these manganese moments, as well as by measuring the magnetization behaviors as a function of temperature. And now these dotted lines are basically the same one that I showed you in the previous slide. These are just the magnetic moments of manganese and terbium. These solid lines are the magnetic anisotropic energy. This blue one is for terbium, and the red one is for the manganese atom. Now, interestingly, what we see is that at high temperature, the manganese moment of the magnetic anisotropy energy of manganese is larger than that of the terbium. This is negative. That's why it favors in-plane orientation. It's positive. It favors out-of-plane orientation. And at 310 Kelvin, they become equal. And below 300 Kelvin, the anisotropy of terbium wins over the manganese. That's why now the moment start rotating from in-plane to the out-of-plane. And that's one of the things that we realized. And now this is about the spin reorientation induced by or mediated by the fluctuation. Another part that we saw the talk earlier also is about the anomalous Hall. Remember, this is a ferrimagnet. If you just measure an iron ferromagnet, then you see anomalous Hall because there is a spin splitting. A ferrimagnet is no different than a ferromagnet. So there is spin splitting in this material. And one of the ways to kind of understand this intrinsic contribution from the band structure is by doing the scaling behavior. And for that, we need to measure the rho xx and rho xy. that was already discussed earlier in this talk, and so that we measured the rho XX, sorry, sigma XX, and then sigma XY, the anomalous part, and we tried to do the scaling behavior here. So in the literature, we have seen a lot of the time this contribution, and in this contribution we have the C part, which is the intercept, and intercept gives the intrinsic contribution. Whereas the A term, which comes with the sigma XX square terms, is believed to come from some sort of impurity scattering, skew scattering, side jump, and so on. It goes into that. But this, when we try to fit in our data, this line, it doesn't fit well, as you can see here. And we, empirically, we try to, do different thing to try to fit into this data. And what we found, interestingly, is that as soon as we add this 1 over sigma XX term to this data, it fits perfectly. It not only fits, but it gives rise to the similar value of this intrinsic contribution as without, as if we were, not using this 1 over sigma XX term. Okay, and then another thing is that it is A sigma XX square is not that important at higher temperatures. See, and if you just remove this A sigma XX square term and just plot this fit this equation, it gives at high temperature, the fit is pretty good with the red one, right? The red and green one. But it deviates only at lower temperature. And remember, at lower temperature, there can be contribution from this A, which is very obvious. But at high temperature, and what is happening in this material at high temperature is the fluctuation. So we thought that this 1 over sigma XX term might be coming from the fluctuation. Well, this is just a one system. Can we claim it? We can propose it, but is that a solid proof that it's coming from fluctuation? Maybe not as convincing, right? But I'll show you another, because we were working on these different 166 compounds, and we're making, other compounds. I'll show you that now we believe that this 1 over sigma XX may be related to coming from the fluctuations. And to just touch base upon this intrinsic part, what we have shown very clearly by doing a band structure calculation, and that matches pretty well with the experiment, is that yes, we don't need the topological phenomena for this. Just the spin splitting at different kz locations gives the Berry curvature, and that Berry curvature is good enough to give rise to LR's anomalous Hall conductivity in this material. Coming back to, again, the question is, what is this D term is, right? We mentioned that there is a fluctuation here, and that we think that this is coming from the fluctuation terbium moment. Now, in order to convince, what I will do is I will show you another material. So the idea is here to get a ferromagnetic system along the C-axis, right? Electromagnetic systems, we could polarize it, but it requires like about 10 Tesla magnetic field. In the lab, it's pretty difficult to do. But what we realize is that when you dope this yttrium with a little bit of gallium, you don't need much. This is 0.55 of gallium. It makes a nice ferromagnetic system. But now remember, this is a disordered system. It's not a very ordered system. It becomes ferromagnet, and the ferromagnet, understandably, the moments will be in the plane, as in the case of manganese. And but the interesting thing is that it doesn't require that much of a field to get polarized along C-axis also. So it's about less than 2 Tesla magnetic field. We can orient the spins along C-axis and get the ferromagnetic behavior that way. Now, this provides us a nice way to kind of test our, hypothesis of whether that 1 over sigma XX term is coming from fluctuation or not, right? This one shouldn't have fluctuation that much because there is no terbium here. It's only manganese, maybe a little bit fluctuation. Now, we measured the anomalous Hall. We can measure it down to 1.8 Kelvin pretty easily. And we did the scaling behavior on this one also. But the shape is pretty much same. And now the question is, is this something else, artifact or something? But turns out to be not that. Just don't go with the shape. Look into the numbers. If we compare the numbers, and it is very interesting and everything coming together very nicely, is that A is coming from impurity scattering and things like that. And in terbium manganese 16.6, you see A, it is 10 to the negative 9 per Siemens centimeter. Look into this one. This is much larger, right? This is the line compound. This is a disorder system. This is what you would expect when you introduce disorder for and to have these impurities carrying term much larger in a system. Look into the C term, which is coming from the band structure. It's 140 Siemens per centimeter in terbium manganese 16.6. In this compound, it's 121 Siemens per centimeter. And it's also understandable because the disorder might have messed up with the bands a little bit. But in a ballpark, it remains the same. And then look into this D term, which we thought was coming from the fluctuation, right? This system should not have as much of a fluctuation as in terbium manganese 16.6. And you can see that the value of D that was 10 to the power 5 in this case comes down to be just about 180. It's a much reduced part. So this term is very, very weak in this system. There may be some fluctuations in the system, but not as dramatic as in terbium manganese 16.6. So this made us think about that. We have been discussing about the anomalous Hall effect for centuries, and there has been several models that has been written theoretically in order to describe this anomalous Hall effect. It's probably one of the most controversial topics, right? So the scaling behavior, we may introduce the effect of spin fluctuation in a highly fluctuating system. We cannot neglect those probably. And the theories may need to work on this to see how the spin fluctuation can affect the anomalous Hall effect. So that's that's all about my talk. So again, the summary or the conclusion is that spin fluctuation is important in 166 compounds, especially when we start putting the magnetic rare earth elements into the system. Topological Hall effect in yttrium manganese 16.6 originates from fluctuation. Spin reorientation in terbium manganese 16.6 has its origin to the fluctuation, and this significantly 1 over sigma XX term of AHE in terbium manganese 16.6 than that in the yttrium compound, suggests that spin fluctuations do contribute to AHC, and that this is the term that's currently not in theory. So with this, I would like to thank you, and I would like to acknowledge my various different collaborators from different organizations without whom I could not have done any of these works. So thanks a lot to all of them, and then thank you also, and I'll take a question from here.
Thanks, Nirmal. That was a very nice talk. So let me quickly ask the first one, which is that you mentioned the fluctuations are happening in terbium, right? But presumably the anomalous Hall contribution is coming from the kagome manganese net, right? So how do these fluctuations couple? Was my question. Like, if you assume that the transport is happening in the manganese, then how does the terbium effect, fluctuation effect? Yeah, go ahead.
So yeah, that's it is not actually right. Did I not? Was I not clear here?
Yeah,
so,
maybe I missed something.
Into the intrinsic contribution. The intrinsic contribution is not changing that much, right? The green term, you see the C.
I see.
Not changing that much.
Okay.
What is coming in one and not in other is this 1 over sigma XX term.
I see. Okay.
And that is something that we don't know theoretically yet.
Okay, so what you're thinking is that the scattering from these fluctuations, is that right?
Right.
Terbium is acting like a scattering center.
Yes.
Okay. All right. I'm still trying to wrap my head around that. Okay, thanks. Bogdan, go ahead, please.
Hi, great talk. So I have a couple of questions. So the ferromagnetism here is also thought to be flat band, or the magnetism, the different. And well, can you confirm that? And then second of all, do we have the spin wave spectrum calculated and all the collective modes?
Okay, the first one.
Also for your theory collaborators or
Sure, yeah, he can jump in, but let me tell you this. The flat band thing is in these materials, the flat band are probably way below the Fermi energy.
Okay.
So, there is a claim in one of the papers that the flat band is observed, but in that calculation, they use this DMFT in yttrium magnetic 10.6 to show the flat band. We don't need DMFT. We have now our own data to explain all the features. The problem with yttrium magnetic 10.6 is that its magnetic structure is very complicated. What people do is that they, do calculation in a forced ferromagnetic state, and then the band structures do not match, and which is obvious, right? So calculation needs to be.
But the flat band is not at the Fermi level in the paramagnetic state. I would expect it not to be okay.
In either.
Yeah,
Okay.
yeah, in either. And can you remind me what was your second question?
If you know the collective modes.
That I don't know.
Can I keep in?
Sure.
So there were completely separate neutral measurements of spin waves for yttrium compound, which they fitted with a standard Heisenberg model and extracted exchange parameters, which are reasonably consistent with the calculated one.
Mhm.
So I don't remember seeing any surprise there. Regarding there's flat bands, first, they are not very flat because the material has considerable hopping across the level. And, this is, as opposed to Dirac band, it's not topologically protected feature. It just appears only if you have particular model. So that doesn't seem to play much role or any role at all. And going back to Anand's question about, yes, that's the scattering of phonons was considered in a seminal paper by Patrick Bruno, and they showed that phonons do not contribute to extrinsic Hall effect. However, that argument was actually based strongly on the fact that phonons are just charge fluctuations. I even verified it with Patrick personally, and he said that yes, the argument would not apply to spin fluctuations. So spin fluctuations have not been considered. What we need a theory similar to Crepio and Pat and Bruno theory for for phonons. We need to do something similar for spin fluctuations, which we haven't done yet. And yes, the coupling is not strong, definitely, but there is a considerable exchange interaction between terbium and manganese. So there is scattering, and in lacking quantitative theory, we cannot tell how much scattering we need to get these numbers. That's the state now.
Thank you.
Great, thank you, Gordon.
Okay, so it's 10:15, so I think we should pick up again with session 2. So I'll be chairing session 2. Again, I'm Rob McQueenie from Iowa State and Ames National Lab. And so the first talk in this session we have is from Ilya Zelkovich from Boston College. The title of the talk is Colossal Orbital Zeeman Effect Driven by Tunable Spin Vary Curvature in a Kagome Metal. So Ilya, the floor is yours.
Thank you very much. Can you hear me okay? Again, just it's good. Okay.
Yes, I can hear you fine.
Thank you. So first, I'd like to thank the organizers for the invitation to speak at a workshop today. So in my talk, I'll tell you a little bit how we can study Berry curvature effects and topological orbital magnetic moments in some of the same Kagome systems that we already heard about today, but using scanning tunneling microscopy and spectroscopy. So here's a brief outline of what you'll hear from me in the next 20 or so minutes. So I will start by telling you a little more about general concept of orbital magnetization and orbital moments in solids, and how our strategy in uncovering these is by measuring how the electronic band structure couples to magnetic field with energy and momentum space resolution. So the technique that we use is, again, scanning tunneling microscopy, or STM. And I will talk about 2 different sets of experiments that we have performed in these systems. So the first one is focused on this yttrium manganese tin 166. So this is a helical antiferromagnet, at least at low temperature. And what was really interesting to us is in this system turns out to be very nice for imaging the prominent band structure of the Kagome lattice. So that involves the Hopf singularity and one of the direct cones. So these are very nicely seen in our STM experiments. And then I will also tell you how we can investigate how basically these evolve or renormalize as a functional magnetic field. So not many techniques can actually be able to measure essential electronic band structure with being able to apply the magnetic field externally and essentially change the magnetic electronic band structure by that. And this is one of the kind of bread and butter of STM. And then in the second part of the talk, I will tell you some of our very recent work on terbium, vanadium, tin 166. So one of the advantages of this system is that it has a simpler magnetic structure. So at low temperature, it is a soft ferromagnet. So it has very low coercive fields. It also has a very low Curie temperature that's very coincidentally around the liquid helium temperature. So it's, again, favorable for STM to essentially study in and out of this ferromagnetic state. And what we found in this system is actually very interesting. So we were able to image one of the direct dispersions that it turns out it splits in magnetic field quite substantially. And what we'll try to argue is, again, due to underlying orbital magnetic moments in these that should generally occur in these kagome materials at certain portions of the electronic band structure. Okay, so it is well established how spin magnetic moments in many materials can give rise to various magnetic orders. But in addition to spin, orbital contributions can also give rise to net magnetization. The theory of such orbital magnetization is also well established now. So here are some of the relevant references where this was put forth. But the basic idea is that the contribution stems directly from the Berry curvature of the electronic bands. So different parts of the electronic bands will carry different orbital magnetic moments. And as such, orbital magnetic moments associated with different electronic states are going to be momentum dependent. So you will see a lot of this MNOK. So this is orbital magnetic moment associated with different band and with the different momentum of the electronic state that can, in principle, be calculated. So another way to think about this is in terms of the effective G factor. So the G factor is something that sets how much individual electronic states are going to shift in energy as you apply the magnetic field. And in most materials, the G factor is very small. So it's something at the order of a fraction of milli-electron volt per Tesla. So in most cases, you will not see any substantial change in the band structure as you apply the magnetic field. But in topological materials, and in particular these kagome systems, what it turns out that this G factor can be substantially enhanced due to non-trivial Berry curvature effects. And this is something that we're going to argue actually underlies many of our observations in these kagome materials. Okay, so beyond theory, once this was established, the experiments first in graphene-based structures try to unveil this orbital magnetization in various forms. So for example, in twisted bilayer graphene, what I'm showing here on the left is actually a theory that calculated orbital magnetic moments for this structure that should primarily reside for states near the gamma point. And then several of experiments were actually attempting to uncover these orbital magnetic moments. So here there's one on also, I believe, twisted bilayer graphene, where based on the dispersion of these lambda levels as a function of magnetic field, one can, the dispersion of these peaks as a function of magnetic field, based on their magnitude, one can actually attribute this to this topological origin, the non-trivial Berry curvature associated with these particular portions of the bands. And then probably a more direct evidence is something that you can get from net magnetization using SQUID. So this is from Andrea Young's group, where they were actually able to locally image this net magnetization in twisted bilayer graphene that otherwise has no spin magnetism. So this is just something that comes from orbital effects. So in our experiment, we set to essentially investigate similar kind of physics in the kagome systems. And I just want to go over this very briefly. I know this is very familiar for the audience, but on the left here, I'm showing a simple electronic band structure of a kagome system. So it's a single kagome plane, and from tight binding calculations, one can see that the electronic band structure consists of direct points at K. There's going to be a Van Holt singularity at M, and there's also going to be a flat band at the top, or I guess at the bottom of the dispersion, depending on the details of the system. So once you introduce a little bit of spin-orbit coupling, some of these crossings actually split. So here, the Dirac point actually is going to result in a Dirac gap, and you also have lifting of the degeneracy here. So if you actually calculate for this kind of electronic band structure, what is the orbital magnetic moment, let's say for this Dirac band here, so the upper part of the Dirac dispersion, you will see substantial orbital magnetic moments concentrated at K. So this comes from the non-zero Berry curvature concentrated primarily at the bottom of this Dirac dispersion. So we wanted to probe this kind of physics using STM. So what is STM? It is a very simple technique that essentially consists of a tip and a sample. You bring the tip very close to the sample of interest, and then you can measure something that we call a topography. So that tells us a little bit about the atomic structure of the system. You can measure the DIDV spectrum that tells us about local density of states, integrated local density of states. And what's going to be relevant for today's talk is this specialized measurement that we call quasi-particle interference imaging, that essentially relies on elastic scattering of electrons and their interference from defects in a material. So you can see that in differential conductance or DIDV maps that I'm showing here. So in real space, it looks like waves. If you take a Fourier transform, you can see the prominent wave vectors. And in comparison with theory, you can actually deduce where this comes from. So what I will show you, this kind of circular signature that we see in many of these kagome systems come from the Dirac cone. Okay, so the first system that I will talk about is this helical antiferromagnet yttrium manganese tin, and this is the layer structure of this system. So it consists of tin slabs that basically have a manganese kagome layer on either side, and this kind of tin manganese structure is sandwiched between these yttrium tin layers that are the gray and blue here. It looks that these boxing crystals are actually nice and layered. They are nice and layered. They're actually quite difficult to cleave. So I might as well mention at this point that I'm out of maybe 30 or 40 samples that we actually attempted to cleave, maybe only like 5 or 6 successfully cleaved to reveal a flat plane for STM measurements. So the way our experiments work, we get these from our collaborators. So this was from Hechang Lei. And then we put them in vacuum. We rip them apart in vacuum to expose a clean surface and put them directly in STM. So these crystals cleave somewhere between these two. So yttrium manganese tin is again this helical antiferromagnet. And then once we cleave it, this is once we successfully cleave it and we are able to locate this large flat region of the sample, this is what a topograph looks like. This is a topograph of the manganese layer. So if you zoom in, you can see this hexagonal lattice of the manganese atoms. And then this is the large scale topograph. So it has this hexagonal lattice that underlies behind, you can kind of see there, and also several different impurities that will actually serve as good scattering centers for our QPI measurements. So the first thing we do when we approach on a new sample, so we measure DIDV spectrum. So this is an average DIDV spectrum on this manganese termination. And the x-axis is bias or the energy, and the y-axis is essentially density of states. And what I want you to focus on in this system is this little peak near Fermi energy. So we want you to investigate the nature of these peaks. So we apply the magnetic field. The magnetic field is applied out of plane. And what we found is that here on the right, I'm showing this peak zoomed in a narrow energy range. As a function of magnetic field, this peak does not split. So if this was some kind of spin degenerate state, one would expect the peak to split into two as you apply the magnetic field. But in both cases here, with the field applied along plus c-axis or minus c-axis, in both cases, the peak just moves. And we can calculate how much this peak moves as a function of applied magnetic field. So the velocity of this dispersion is something as 0.3 millielectronvolts per Tesla. So this is much higher dispersion velocity than what you would expect from a conventional kind of a spin G factor that's, you know, maybe 5 to 10 times smaller than this. And again, the fact that spectral peak does not split leads us to believe this is a spin polarized spectral feature. So in addition to this kind of momentum integrated technique, what we wanted to do is we wanted to gain insight into momentum information of the electronic band structure. So for that, we use this QPI measurement. It is imperative for this to have a large kind of topograph that you can measure. And then this is exactly what we have here. And then we measure DIDV map. This is the one acquired at the Fermi level exactly. And then we perform the Fourier transform. So the Fourier transform of this image on the right leads us to get just like a single circle centered at the center of the Fourier transform. So this is what a complete data set looks like. On the left is a raw DIDV map. On the right is a Fourier transform of this map. And what you see as the ripples on the left get smaller, the circle on the right gets bigger. And we can span, you know, kind of a substantial energy range, at least for the purposes of STM, that crosses the Fermi level. And the summary of what we get from STM is basically shown here on the right. So in the color plot here, I'm showing the angular average of the Fourier transforms that I've shown on the previous slide. So you can see something that looks like a Dirac cone. And then here is a DIDV spectrum. So what we do to actually infer what this is coming from is we compare to the calculations in comparison to ARPAs. So based on the dispersion velocity that we see here and based on the energy, we attributed this dispersion to the Dirac dispersion right there. And then this peak here that actually occurs maybe like 5 millivolts below the bottom of this Dirac cone here is likely the saddle. So from this is kind of the identification of the spectral features. And next, what we wanted to see is how does this QPI signature of the Dirac dispersion change in magnetic field? So from 0 Tesla, I'm showing how it changes to 2, 4, 6, 8, and so on. So the summary of all these schematically depicted is here on the lower right. The first observation is that this Dirac cone does not split. So if you have a spin degenerate state, you would expect maybe one thing to go up, the other one to go down. But here, both of them actually just move. The dispersion just changes, and you see more of the rounding of the bottom of the Dirac cone here that kind of moves upwards. So at the very least, what you can see from this measurement is the energy of the individual electronic states actually changes at different speeds for different K points. So it's more substantial at the bottom of the Dirac cone. And to look at the explanation for this, so we explored two different scenarios. So one is related to these orbital magnetic moments related to the Berry curvature. And the other one is something that was proposed in RM10, where due to spin-orbit coupling and tilting of the spins, you essentially round up the Dirac cone by increasing the Dirac gap. And in this system, it is a helical antiferromagnet. If you measure the magnetization as a function of applied magnetic field, you will see you will just get essentially spin tilting. So in this system, we cannot distinguish these two scenarios, which is why we turn to the second system. So the second system is unlike this ECM manganese thing, where you have a single spin polarized band that as you apply the magnetic field, so it might shift upwards or downwards. In our case, it shifts upwards. And then on the right side, I'm showing what I will explain more, the case of terbium vanadium tin, where you have a nearly spin degenerate Dirac cone. And then even though it's spin degenerate, you still have spin Berry curvature, primarily at the bottom of this Dirac dispersion. As you apply the magnetic field, you will see is you actually get a splitting. So we see two spin branches of the Dirac dispersions, one moving up and the other one moving downwards as a function of magnetic field. So the reason why we chose terbium vanadium tin is actually it's a nice soft ferromagnet. So BTC of about 4.1 Kelvin. And it, unlike yttrium manganese tin that we just started at the beginning of pandemic, is one of the systems that we just had lying around, and it turned out to be very interesting. This was very targeted because both the Curie temperature and the coercive fields are well within the range of STM. So this is what the electronic band structure looks like here. And with help of our theory collaborators, we were able to calculate the spin Berry curvature of different bands. So similarly to what you get in a simple case for a single Dirac dispersion, we have large Berry curvature concentrated at very special points. So what we do now is basically perform the same experiments that I've shown you on yttrium manganese tin. We locate a clean region of the sample, and then we take DIDV spectrum. And here I'm showing the region, the energy range of the DIDV spectrum, where we see most prominent changes with magnetic field. So I'm going to check this feature as a function of magnetic field that kind of, you can see, shift and merges into this main feature there. So this is summarized nicely here on the right. E star is the position of this peak, and the x-axis here is a magnetic field applied out of plane. This is a different temperature, so it's 2 Kelvin, 4 Kelvin, and 10 Kelvin. We investigated the dispersion of this feature, and what we note is that in this system, the dispersion of this feature continues well beyond the saturation of spin moments. So this was our first hint that there's something unconventional happening here. So the HC here is about maybe half a Tesla, but here we have the dispersion to about 2 Tesla, even more at this higher temperature. So we wanted to investigate this further, and then we performed the same QPI measurements. Again, you see a circular pattern in the center of the Fourier transform that disperses as a function of energy. We plot in terms of this radially average Fourier transform. So this is the STM data here on the left. You can see the Dirac, this dispersion actually occurs at positive energies, which is something that would not be accessible by RPES, but we compare this to theory, and this is what theoretical calculation tells us. So if you compare the dispersion that we get and the dispersion that you would get from DFT calculations, it matches very well. So as the kind of last part of the experiment, we wanted to examine how this thing evolves as a function of magnetic field. And this is what I'm showing you next. So the top row are basically the same QPI measurements as a function of magnetic field, the same region of the sample, the same STM tip. On the bottom is this processing of the image above, which is something that RPES measurements also often use. It's essentially taking the second derivative. So what you will see is that this single band actually splits into two, becomes more and more prominent as you increase the magnetic field. And this splitting is actually quite substantial. And what I want to show you is there are several ways one can quantify this splitting. So one is from the simple DIDV spectrum, how it changes as a function of magnetic field from this one peak to two peaks. So this is what I'm showing here in this DIDV third derivative, where one peak splits into two. We can quantify that both for the DIDV spectrum and for the splitting of this momentum space Dirac dispersion that you see here on the left. In both cases, this is essentially the summary. So the splitting from 0 Tesla to these higher fields is from, I guess, 0 millivolts to about 50 millivolts. So the splitting is at the order of 50 millielectronvolts, which is enormous. And we can directly see that from the momentum resolution our STM has, that it relates directly to the splitting of the Dirac dispersion. So by conventional, spin G factor, one would need several hundreds of Tesla to achieve this. So we can nicely attribute this, and we collaborate again with the same group of theories to a picture of these topological orbital moments that are most concentrated here at the bottom of the Dirac dispersion. So the spin degenerate Dirac cone as a function of magnetic field splits into two different branches. And you can even see based on the shape of this one and that one, it kind of looks like what you would expect from essentially how the orbital magnetic moments would shift the bottom of the cone primarily, and then this effect kind of as you taper towards or away from the K point, that effect actually tapers down. So this is the first as far as we're aware, direct experimental evidence of these orbital magnetic moments with momentum resolution. So again, this is something that's increasingly different for many other probes. Since I'm basically out of time, I just want to briefly summarize that these 166 systems are very interesting from the perspective of STM and imaging how the electronic band structure changes the magnetic field. So this ETM Magnetism, the first system that I've shown you, we simply were not able to distinguish spin canting for any sort of topological effects. But in terbium vanadium tin, due to how the electronic band structure change evolves to much higher field to any sort of coercive fields that exist here, we can nicely attribute this to the underlying Berry curvature effects that give rise to these topological orbital magnetic moments. These are all the collaborators involved in this work. Hong, one of my students, actually took most of the data that I've shown and also made most of the slides that I'm also showing today. We got the samples from Stephen Wilson's group and Hechang Lei's, and we have a long list of collaborators that help us in interpreting our STM data. Thank you very much.
Great. Thanks, Ilya. So we have one question in the chat from Igor. Igor, do you want to ask, or do you want me to read it for you?
No, just read it. It's fine.
So why should we expect splitting of the peak if the field is applied perpendicular to the magnetic moments? I assume you mean for the yttrium manganese case.
Yes.
Yeah, I mean, so it's unclear why it would be. So yttrium manganese tin is something that's kind of a remarkable experimental observation that we do not have a conclusive explanation of why that might be. So it's since the spins in yttrium manganese tin, as you apply the magnetic, so it's again this helical antiferromagnet, as you apply the magnetic field, they might can't. In principle, there could be some effect, even if you can't really pinpoint it exactly, as you can't the spins,
Okay.
they can contribute to the band structure changing. At least
Fair
that's
enough.
that
Thank
would
you.
be more honest, yeah.
Thank you.
Okay. Okay, so Nirmal, do you want to go ahead?
Hi, Ilya, thank you for the wonderful talk. So, my question is, more broadly, not specific to these materials, is, you said that you have this momentum resolution on your STM. Does QPI also have the momentum resolution when you measure, or is there, how does it work? It's just.
So the QPI is basically what allows us to have the momentum resolution, and it's something that you can think of it as like ARPES using STM. So it's except ARPES can give you this band structure for all the bands for most materials below, I guess the Fermi level. STM can only get you for specific cases. So we don't directly measure the electronic momentum. What we measure is scattering. So that means you have an electron coming in with some momentum, and then scatters off a defect in another direction. And then these two waves essentially interfere and give us these standing wave patterns in STM. So basically what we see is not momentum, but momentum transfer. It's, I glossed over that for the interest of time, but momentum transfer. So what we see is essentially if you have a constant energy contour that's just like a single circle, we see a backscattering wave vector. So this is what you see in STM. But in STM, Fourier transform is also just like a single circular contour. It probably gives rise to like a circular contour in momentum space. Again, if the dispersion velocity matches to, for example, ARPES or theory and so on. So it is an indirect measure. I mean, I'm not trying to say that we're better than ARPES. We're certainly not. But we can apply these substantial magnetic fields and see how this changes magnetic field, which is basically the main strength.
Sure. Thank you.
No problem.
William, did you want to go ahead?
Yeah, so I'm really enjoying this. I think this is a really cool way of looking at that splitting. So in the terbium compound, you showed the splitting magnitude versus field. Yes.
Yeah.
On the top right and also the bottom right, it flattens off. It's
Yeah.
What's up with that?
Yeah. So one way to understand this is, and we thought about this long and hard. I mean, the short answer is we're not completely sure why it would completely saturate, but I can give you like a kind of an answer why it would taper off, so why it would become slower. So if you think about if you have a Dirac dispersion and you gap it with a very small gap, so the Berry curvature that is proportional to these orbital moments is going to be very large. So you can think of it as inversely proportional to the gap. Okay. So if you apply magnetic field, so you basically round off this bottom of the Dirac cone, you can think about, Berry curvature becoming slightly smaller at the bottom, therefore the orbital moments are smaller, therefore they couple less with the field. This is not something we could directly, or at least our theories couldn't directly compute this, in a full kind of scale model, but this is the gist. I still don't completely understand why it tapers off by 4 or 6 Tesla. It is a mystery. Maybe it's just too small to be resolved, but it certainly persists to these very high.
Can you see any other bands moving around, or are these the two that are having the big response?
These are the biggest ones, yeah. So if you look at the DID spectrum, and we checked like the rest of the range, I mean, there's nothing substantial. And DID spectrum is something that integrates over everything, and the band structure is kind of like messy. So that's
I'm
why
aware, yeah.
But then if you just, what we really saw is like what's prominent in this system is this Dirac dispersion. So now we've imaged in 2 different materials, and it seems like the 166 are, it's not something that you can see in other kagome systems, actually. Like we studied a lot of these AVS kagome superconductors, and, we don't see like the flat bands there in STM or the Dirac dispersion. You see other bands, but not this nice kind of Dirac cone that you can see here. So this was very cool.
Okay, thanks.
Great. So Ilya, thank you so much. So now we'll move on to the next speaker in this session. So now we get a chance to hear a little bit about theory of these materials. So Andre Bernevig from Princeton University will give the next talk titled Remarkable Nature of the CDW in Scandium Vanadium 610-6 and Faithful Lego Block Electronic Hamiltonian of the 166 series beyond the Kagome principle. So Andre, whenever you're ready, go ahead and share the screen.
Thank you. Very long title.
Yes, I can see your slides and I can hear you just fine. So go ahead.
Fantastic. Thanks so much for having me. Basically, this is a field in which we started working on it recently because the attraction was too strong to resist. But it's going to be half a theory talk, but it was inspired by an experiment. And then, of course, it was inspired by trying to figure out something about these materials. Of course, a lot of it has already been figured out by people in this Zoom. Now, of course, most of the work here has been done by Haoyu Hu, Yi Zhang, Dumitru Kaluguru, and more recently, Xiaolong Feng. But the experimental part has been done by David Subirez and Santiago Blanco Canosa with samples from Claudia Felsa's group. So I'm going to basically tell you kind of what I got into this field. Basically, at some point, Joe Kelsey kept talking about flat bands about 5 years ago. So I started trying to look into them. And as I looked into them, there were more and more experiments and theory. And by the time we started working into it, there was already a huge amount of data and theoretical analysis, which basically solved a lot of the features of these systems. But basically, the major interesting thing about the systems that we've heard so far is the fact that there's topology and correlations in these lattices. And now I'm going to argue that basically similar things can happen in, for example, phonons and electron phonon coupling. So I hope I cited everyone, at least everyone in this Zoom. And I'm going to now go to the main part of my talk. Basically, towards the end of the talk, I'm going to try to give a faithful tight binding model of these orbitals. And I'm going to try to argue that the Kagome principle is certainly incomplete to describe the flat bands in the systems, and that we have tight binding models which faithfully reproduce them and provide electronic structure, if I get to this. But before this, I wanted to start with the system that basically attracted our attention. And this was the Scandium Vanadium 610-6. which basically doesn't have any flat bands at the Fermi level. It doesn't have magnetism. Well, there's a new paper that basically claims some magnetic fluctuations, but so far, at least as far as I know, no magnetism. And the Fermi level is at a Van Hoff singularity. Now, or close to Van Hoff singularity. It has a CW state, and the CW vector is 1/3, 1/3, 1/3. The Van Hoff singularity is not the CW vector. And the experiments of my collaborator, Santiago Canosa, basically showed the diffusive scattering maps, which basically showed a collapsing phonon in a second order phase transition type at 1/3, 1/3, 1/2, called also the H point here on. And you can see the collapse of the phonon around the CW phase transition at 1/3, 1/3, 1/2. And you can see the fact that the 1/3, 1/3 phonon does not collapse here. And the CW is at this wave vector. So trying to explain this, what I found at the time, and I still find quite remarkable experimental fact, is what we're going to try to do, what I'm going to try to present now. Now, we're looking for, nesting origins, etc. But you look at the total susceptibility, and there is no peak at the total susceptibility at the CW wave vector. So this can't be the explanation, at least for the total susceptibility. And then, of course, a lot of the work that we did, was based on E's and Xiaolong's models for phonons that basically get you the phonon spectrum at low temperature and high temperature. And these high temperatures are basically very, very high temperatures for the CW, but basically they give you the phonon spectrum supposedly in the non-CW phase. So these is left is low T. You can see a clear kind of negative phonon on entire plane around k is equals to pi, with a minimum at the H point, but it's a soft minimum. And then the high T above the CW transition, you can see a very flat band around the same plane above, hardened obviously. Below the CW transition, the phonon spectrum are also hardened, but here's the above high T, you can see this phonon spectrum, and you can basically ask a zeroth order question: how do I get from right to left? How do I explain from right to left? And the second order question is why, even though the phonon is the minimum is at H, the CW is actually at K bar, so 1/3, 1/3, 1/3. So I'm going to gloss over a lot of details, but what we try to do is kind of a combination. Obviously, we have the DFT and the first principles, but to try to get an understanding and a modeling that's a little bit beyond that, hopefully. So basically, we first try to get this phonon to see where it is localized. And it's a phonon the one that goes soft in a second order way in the experiment, the one at the H point. And it's a phonon localized onto a trigonal tin. It's at momentum pi, and it's actually very flat in plane because of the way the trigonal tin couples to, for example, the kagome. And its model is basically, and this you can theoretically justify, not only by ab initio, but by just building a force model constant, seeing that I see your hand, Igor, but if you have a pressing question now, otherwise I'm gonna ask for more time.
Never mind. It's just for me not to forget to ask question.
Okay.
After.
So the model here is that of an SSH chain, basically. So it's very flat in plane, but it's got SSH couplings out of plane. And the phonon, as you can see, is at momentum pi, and is the even phonon with respect to the unit cell in plane. So it's the even wave vector. So now, in order to understand the softening of the phonon, we must get a handle on the electron-phonon interactions. Now, as you can imagine, this is a very complicated system. It's got a complicated band structure, and it's got a complicated phonon band. So how can we even attempt to make an analytic model of the electron-phonon interaction? Well, at least for these orbitals that are appearing here, which I'm assuming that since I have tin, basically the tin phonon is going to interact strongly with tin orbitals and or more strongly. So basically for these type of PZ type orbitals, you can basically make a electron phonon model that's justified by some Gaussian approximation. It's not always true, actually in most cases it's not true when you have angle dependence of orbitals. But what basically we're saying is that the phonon in charge of this CW transistor will couple the most strongly with the electron of the same symmetry that has the Vanier center where the Vanier center of the phonon is. And this is a principle that's basically based on, you know, some quantum geometry, which is basically a fancy way of quantifying Vanier centers. But it basically gives you, and you can justify it by, you know, assuming no angle dependence, which for S and PZ orbitals can be correct, of your hoppings, and some sort of a Gaussian approximation. And then if you take the derivative of the hopping, it's exactly that coupling of two Vanier centers. And if you take this electron phonon model, which is basically the even phonon within the unit cell coupling to the even combination of the electrons on the two tins, two trigonal tins within the same unit cell, then you're in business. You have an electron phonon coupling that's analytically tractable. And now that you have this electron phonon coupling that's analytically tractable, you can compute the self-energy of the phonon induced by the bubble. Okay. And what you can do is with this electron phonon coupling, which is very, very easy, which basically neglects, well, it neglects all the other electron phonon couplings. So for example, it is not going to give you any good spectrum for the higher bands, but it should give you a good electron phonon coupling between this phonon, the Gauss soft, and the electrons present in the tin. Okay. And for this, you can immediately see that if you do the bubble in a perturbation theory, you can reproduce the low energy, the negative phonon spectrum of the DFT by just doing the bubble corrections to the phonon spectrum. This red is perturbation, the lines are the DFT. So what we do is basically we know that in the infinite T limit, you get a flat band that's hard, that's above T equals 0. We know that, and we understand this because this phonon sits, trigonal phonon sits it goes out of plane, and we know that the corrections to low energy, to low temperature are given by the electrons, and we compute these corrections, and you get what I think is a pretty nice fit to the DFT band structure. Now, this fit has several properties. For example, now you can see that the H point is the lowest. And this property, you can understand it immediately from just the susceptibility of the trigonal tin. So as I mentioned, there's nothing to do in the susceptibility of the entire system. It's got no features. But if you do the orbital, which we're just looking at the electron phonon coupling of the tin with the tin orbitals. If you look at the tin susceptibility, what you're going to find is that the tin susceptibility can be basically separated into two contributions: an on-site contribution that basically lowers the photon energy below 0, well, omega squared below 0, and then a nearest neighbor contribution that's basically the hopping on a triangular lattice, which is made by triangular tin, hopping on a triangular lattice, which gives the dispersion of the phonon. Okay, you see it's a little soft here, soft minimum at H. That's just a triangular dispersion. If I was looking in this plane here, this would be just a triangular dispersion of the phonon, which is given by the nearest neighbor of the susceptibility of trigonal tin. Okay, so now we can explain sort of, well, obviously helped by DFT. There's no way we could have done it without DFT, but we can explain in some sort of a semi-analytic way the reason for the softening of the phonon in a second order at the H point. But we know that the real CW is at momentum K bar, which is 1/3, 1/3, 1/3. So what's the scenario? And this is a scenario, of course, because we cannot exactly know what happens, but it's a scenario, it's a consistent scenario where that can happen. So why would it appear in a different wave vector? Well, the H phonon if you write in the Ginzburg-Landau, has an order parameter that has no cubic term. So it's going to have a second order phase transition. But the K phonon, because of momentum conservation, can have a cubic term. And this is just related to the fact that a third adding 3 1/2 momentas in the z direction does not give you momentum 0, but adding 3 1/3 momentas in the z direction can give you momentum 0. So the complex phonon at K, or the 1/3, 1/3, 1/3 can have a cubic term, and it would have a first order phase transition. Now, if you couple them, if you couple the H phonon with the K phonon, what you get is still that you would have a second order phase transition, at least at saddle point. But if you introduce fluctuations in this phonon phi, which fluctuations do exist due to the fact that this phonon has almost a flat band, not an exact flat band, but almost a flat band, these fluctuations actually induce a first order transition in the K phonon, very close to the second order transition. And actually, as the band flatness becomes exact, they actually merge in a logarithmic way, so you won't be able to see it. So we claim that this is a scenario where the K point, 1/3, 1/3, 1/3 A bar point, is actually the first point closest to H, which can get a cubic term, and hence a first order phase transition. And the coupling between the H and the K point phonons, and the fact that the H point phonon is flat, can induce the first order transition in that seen in experiments, and the phonon and the CW at the wave vector K bar. Now, I think I have like 5 more minutes, and I wanted to basically finish with the phonon story, which we claim matches the experiment, obviously, and try to give you a little bit of a hint of how we're trying to build orbital models. And these are orbital models for the paramagnetic state. And I'm trying to convince you that there is physics beyond kagome. So basically, the idea is to try to fit this complicated spaghetti of bands with some actually time binding models that are quasi-simple. Now, as we've seen in many talks, usually these are just fitted with s orbitals on kagome. Now, I want to point out that there's a germanium here in the trigonal lattice. Now, if you have a kagome lattice, okay, and the kagome has obviously a flat band, if you put something in the trigonal lattice and couple the kagome lattice to a trigonal lattice, you're not going to get flat bands anymore. That's the line graph principle. You're smashing up the line graph principle by putting a trigonal kagome, trigonal lattice, so you're not going to get flat bands. Now we can argue, that there's weak coupling between these, but we'll see that on effective models, there's actually not such weak coupling between iron and germanium. So what's the principle? Well, still kagome is of course very important, but we argue that this spaghetti of bands that you get at the Fermi level, and by the way, here you can see the red is is our model, the dots are the DFT. So the matching is not that bad. So how do we do the matching? Well, first of all, what we do is a separation of orbitals that's basically half based on symmetry, half based on chemistry. So it's not an exact symmetry because the orbitals shouldn't be separated by mirror at finite momentum, but it's almost as good enough as we saw because it fits the data. So what we see is that you can, at first order, separate the Hamiltonians to 3 groups. The first group is basically made by the in-plane orbitals, pxy and dx squared minus y squared dxy. The second group is made by dxz and dyz orbitals, and the third group is made by dz squared, and some combinations of them with germanium orbitals in this case, for example. Okay, and of course, even by eigenvalues, H3 would, by mirror eigenvalues, would communicate with H1. But we find that at least to first order, this separation is very good just because of in-plane and out-of-plane bonding. So now there's a principle of building Hamiltonians for each of these groups. So you already separated the spaghetti of bands into 3 groups. There's a principle, and the principle gives you basically deformed flat bands. But I want to point out several things. So I'm going to talk about this second point. So the principle is basically the same as Lieb's principle, which is that of sort of bipartite lattices. So basically, it's telling you that if I have two lattices of different dimensions, you're going to get a bunch of zero modes or a bunch of flat bands. Some of them are not going to be zero modes, and you'll see here. Now, I don't have time to go into many details, but the point is, for example, for this second block, and the second block is the block of the XZ and YZ orbitals and some other orbitals of tin, some of germanium, some hybridization. But the point is that that these unperturbed Hamiltonians, which are kagome, which, for example, HD4 would be an unperturbed kagome Hamiltonian, have a single flat band. HD3, D4 and D3 are XZ and YZ. HD3 would have a flat band. They do couple to other terms, and these coupling terms, which are called S, they actually don't have small values. I mean, they have as large values as the in-plane hopping of the D4, effectively. And then what you find at the end of the story is that you're going to have flat bands or real flat bands only on some lines. So for example, if we look here, we have a flat band, and this is actually, you can see it in Ricardo Comins, and I think Joe is also on the paper. You can see it in the RPES of those papers, actually. There's flat band and of course, Ming Yi, who has, I think, the best data so far on this FEGE, but you can see it on these compounds, and there's clearly some dispersion. It's very flat on some lines, and you can understand this from these Hamiltonians. There's some dispersion on some line on the other lines, and in some of the initial data on FESN, I think that came from Ricardo Comins' group, you can clearly see this. Now, what I want to show you is in the last 1 minute, I think, I want to show you that these models give you not only the flat bands at the Fermi level or flat bands on some lines, but give you the other flat bands also, which are important in other compounds, because in other compounds, the Fermi level is somewhere else. For example, look, this is H1. This is the Hamiltonian x squared minus y squared and y and xy. Now you can see that there's flat bands at the Fermi level, but you can also see that in the DFT, there's flat bands below the Fermi level at -2. And this Hamiltonian, this is our tight binding Hamiltonian. It's basically is a deformed line graph. It's a deformed bipartite Hamiltonian. And you can see that it clearly gives you these flat bands. Moreover, it gives you the flat band around energy 1, which is important in other compounds, some nickel compounds that we'll put out soon. Now you can also see, again, this is H2, that you have flat bands again below the Fermi level also. And these models, for example, kagome, just the pure kagome principle will not give you these flat bands. Okay, these two flat bands here. So I would like to claim that these orbital models give you a faithful description of the physics in at least of the electronic bands in FEGE, FESN, Cobalt SN, and many others, because now, as Igor basically pointed out early on, you can basically, or early on at least in this meeting, you can basically take this structure. They're basically isostructural, so you can take this FEG structure, put a lot of planes of FEG, put some materials in between them, put some atoms in between them, and do perturbation theory and obtain the band structure of all these 166 or a lot of these 166 compounds as basically perturbations of this Lego block of FEG of this band structure. And you can see clearly that they have the same features, at least en masse. So with that, I'd like to thank you for your attention and leave the page of the people that actually did all the work on the screen. So thank you very much.
Great. So the next talk in this session is given from Joanna Blauat. She's a postdoc in CATS down at Los Alamos National Lab, and title of her talk is Pulsed Magnetic Field Studies of Topological Magnetic Kagome Compounds. So Joanna, I see your slides. You probably go into presentation mode. Great.
Okay.
And I can hear you too. Go ahead.
Okay. So as Rob said, my talk will be about the high magnetic field study of some topological magnetic kagome compounds, and starting from the point why did we choose that family to study and the high magnetic fields. the reason is quite obvious, already mentioned earlier, that this is a great family to study the interplay between topology, magnetism, and the strong correlation. So first of all, as we already seen this earlier in many talks, it shows all the relevant feature and the band structures, such as flat bands, which are responsible for the strong electron correlation, but also the Dirac cones, which bring non-trivial topology. The interesting point over here is that many of these materials show very strong complex magnetism, and as we know, the long-range magnetic order might break the time reversal symmetry, and as a result, we might be able also observe the wild state and those family. It also shows the Van Hove singularity, which causes the instabilities in the system, which may result in the long-range magnetic order and also in the superconductivity. So from this, I would like to point that these materials will have a great potential to study, first of all, the complex magnetic phase diagram, and also to investigate how those different magnetic spin textures will influence the possible topological properties. So here is the structure of this material. What we can see that the manganese forms the kagome lattice, which is separated by the rare earth ion. And the interesting point over here is that we can see variety of the ground state from gadolinium and terbium, which are the ferromagnetic material, and ending on erbium, which shows an antiferromagnetic ground state. It was also there was also some prediction about how the gap and the Dirac cone depends on the rare earth ion. So the interesting point in this paper, which was also mentioned in the first talk today, is that what we can see that the magnetic properties of each of this material very strongly influence the transport properties. And that's what we can see at the erbium compounds, for example, which is an antiferromagnetic material. And then when we move to terbium, which is the ferromagnetic material, show a very huge hysteresis, which also influence the Hall effect result. From the other hand, the lutetium, which is a non-magnetic material, it shows a very linear Hall effect. So what was interesting for us in that case is that all those rich magnetic phase diagrams strongly influence the transport properties and also might have the influence for the topological properties of those material. However, from at least up to my knowledge, they were very intensively studied in the low field, but there is not many reports about this family of material in the high field. From the other hand, this is a very rich family when we have many compounds. So to decide from which compound to start and which one might be potentially the most interesting from our high field perspective, we use some of the theoretical calculation to predict some of the magnetic phases and then help us to decide what is the good material to start with. So the theoretical calculation were the mean field calculation, which we got from Rob, and I believe that he include in his Hamiltonian many different parameters, such as exchange interaction between the manganese and the rare earth and manganese ions. He also check out the influence of the crystalline electric field parameters, as well as the Zeeman terms for applied magnetic field. Now, as I mentioned earlier, since there is a variety of the different ground states, for example, for gadolinium and terbium, those calculations seems to be relatively simple to predict the magnetic phase diagram, but it becomes much more complicated in cases like erbium, when all the interaction become much more anisotropic, and also we have to check out all the crystalline electric field parameters. So the first material which we wanted to start is the helium manganese 6-6, and what we can see and the theoretical phase diagrams which we got from Rob, that there is variety of magnetic phases. We come from some planar ferromagnetic, uniaxial ferromagnetic, vertical planar, but also first ferromagnetic. When we look at how it should look like along with the magnetic field along the A and B direction. There is not much difference. However, as we point out on this direction, we can see that that transition is the first order and becomes the second order above the 30 Kelvin. There are also some of these phases which are predicted at such a high field, which is probably above our current limit to measure. And also the interesting thing is what actually happening when the magnetic field is applied along the C direction, because there is the predicted that that transition over here will end up in a critical endpoint. So with those predicted theoretical phase diagram, we wanted to check out how well it will match with our experimental data. So what we started doing is to measure the magnetization. So to measure the magnetization in the high field, we put a small tiny crystal to an ampule. That ampule has around 1 millimeter of a diameter. And what we actually are directly measuring is the magnetic susceptibility. The advantage of this is that we can clearly see all the sharp peaks which reflects the metamagnetic transition, which are much more visible in the DMDH than they would be in the magnetization. So it is very useful in terms of studying phase diagrams. So over here, I can see clearly 3 peaks between 20 to 27 Tesla, which we can see over here looks much smaller in the magnetization. And there is also a very clearly sharp peak around 57 Tesla, which reflects also a higher transition, which is actually not that visible if we look at the magnetization. So making many curves like that at different temperatures, we are able to actually form the phase diagram of this material around the A direction, and we can see that it actually works pretty well with the theory, with the transition going around 25 Tesla. However, we do see some of the smaller phases, which are most likely coming from the same transition but different the growth of the domains. We can pick up also some of the higher transition which might reflect that one. It just experimentally maybe you are observing this at a little bit smaller field. But coming back to the more interesting part with the magnetic field along the C direction, again here is the ampule with the crystal inside. And when the magnetic field is applied along the C direction, we can see the 3 peaks and the very sharp peak around 45 Tesla. So the interesting part and the advantage of studying the magnetic susceptibility in that case is that we can actually see how that critical, the possible critical endpoint will look like in this material. And when I measure just zoom on that region, on that peak around 45 Tesla and how it changes with the temperature, we can clearly see that both of these peaks are always very sharp and very well defined, and just become smaller and smaller as I go towards the higher temperatures. And finally, it disappears around 108 Kelvin. So when we look at the experimental and theoretical phase diagram, we again can see that the predicted critical endpoint actually do exist, that I think we are pretty well matched in terms of the magnetic field because it is around 47 Tesla. However, we do see it 108 Kelvin instead of 50 Kelvin. So that was a first example which we studied in the high magnetic field and try to investigate the magnetic phase diagram. The other example which we thought will be interesting is the terbium vanadium 16-6. This is the one of the icing ferromagnets with the transition temperature at 4 Kelvin. In that case, to measure this along the A direction, we just needed 1 crystal placed in an ampule. However, since the crystals were very thin, I stacked together around 10 to 15 pieces in this ampule to measure it along the C direction. So this time, starting again from the theoretical calculation, what we can see over here, that looking on those level, we can clearly see that this is a uniaxial doublet ground state. We were very well separated from the excited energy by this delta. And the interesting thing is happening when we go towards the high magnetic field, where this excited state crosses together with the doublet before the doublet actually is splitting. So this is the place when there is a predicted metamagnetic phase transition at around 27 Tesla. So what we did, it again turns out that the theory works pretty well in terms of defining the transition at around 27 Tesla. There is some discrepancy, like I see 3 very small transition in 8, 12, and 17 Tesla before that huge metamagnetic transition in 27 Tesla. We also noticed that the slope of M versus H is much steeper in our experimental data than it looks in the theoretical prediction. So I believe what Rob started doing is to try to estimate the G factor out of our experimental data, and based on this, and also try to adjust the crystal electric field parameters. And finally, the pink line is how looks his theoretical prediction and how well it matches our experimental data. So I think right now we are quite consistent, except those 3 little steps. And as we look at the magnetic field applied along the C direction, it was already shown earlier that it has a very sharp transition in the low field and then stays saturated up to 60 Tesla. However, what we noticed and was not previously reported, that at the low field and very low temperature, there is a very huge hysteresis. We can also see that there is a plateau which exists around the 1/3 towards the saturation. And also there is a huge diamagnetic signal at the very low field. As the final project, and actually the most complex, which we measure in the high field, is the erbium manganese 6. Tin 6, and with this we got some neutron diffraction data, which I believe Ben will be talking later about this. The interesting part over here is that we were discovered that there is a transition from a planar ferromagnetic to distorted triple spire magnetic order at around 91 Kelvin. And again, with the theoretical calculation, we were able to find out that the magnetic field diagram along the C direction looks very interesting and is forming some bubble with this vertical plane canted phase enclosed. So we figured out that that might be a great example to study and investigate in detail all the magnetic phases in this compound, and also check out if it will have any influence for the topological properties. So in that case, I got the very huge crystals from Paul Canfield and Tyler Slade. So out of this one huge crystals, I was able to cut it the way to measure it along all 3 different crystallographic axes. So by cutting it here, we use the crystal to measure along A direction. Then by cutting around 30 degrees from this dead piece, we use to measure along the B direction. And then what was left, I cut out and push into this 1 millimeter diameter ampule. So again, as I mentioned earlier, what we are actually probing is the magnetic susceptibility. And over here, we can see the difference between the rising and falling field. So this also will suggest me that there may be some hysteresis. When we look how looks the magnetization, actually, so there is a transition around 25 Tesla, which is represented by this double peak over here. And there's also one more transition around the 55 Tesla. So when we take a closer look, how does it changes along the A, B, and C direction? So this is the A direction, which I just shown. The B direction so shows many more transition and also very small details. And the C direction has again the transition around the 25 Tesla, and it is followed by the 3 little transition. The interesting part over here is that what we notice is that none of these magnetization curves actually saturates up to 60 Tesla. They all stay unsaturated and pretty linear when we are close to our magnetic field limit. So I would like to go quickly through each of these directions, and what we can see over here, that when we increase the temperature with the magnetic field along the A direction, we can see that these two transitions are actually getting closer to each other when we apply when we go towards the higher temperatures. And at the very high temperature, like 50 and 100 K, there is only one transition which is kind of smoothly getting smeared out towards the higher temperatures. The interesting part is that at the low field, when we are above that transition around 91 Kelvin, we can see that there is a hysteresis which is showing up at the low field and becomes bigger at the higher temperatures. So by making many of these curves, this is how looks the phase diagram of the magnetic field applied along the A direction. So these transitions which were merging together actually formed that bubble, which were predicted in the theoretical calculation. We can also see that above the 91 Kelvin, most of the interesting thing which is happening are only in the low field. When we move towards the B direction, which is actually very different from the A, I zoom out that part between 20 to 30 to show that each of those transitions is actually splits into little like double to transition, has a little bit of a structure inside. The interesting thing over here is that when we go higher with temperature at 20 Kelvin, there is one more transition popping out right at the limit of our magnet at the 57 Tesla. And again, at the higher temperature, it just gets smeared out. So over here, we again see a bubble, which is inside the other bubble, but nothing is really happening in that direction in the low magnetic field region. When we apply the magnetic field along the C direction, as I showed earlier, we have one transition around 25 Tesla, which is with the hysteresis, followed by the 3 different peaks. Again, in that case, when we are above the 91 Kelvin, we can see that in the low field, there is many multiple steps and new transition which are showing up. However, in the high field is just that transition which is getting slowly pushed into the higher field. The interesting part over here is that we do not really see fully the bubble. What we think is just the bottom part of this over here. And I would like to show all of this magnetic phase diagram, which we're able to observe experimentally, which are shown on top, and the theoretical prediction, which are at the bottom. So first thing which we can see over here is that there is more transitions predicted at the even higher magnetic field, which we were not able to see it. And as I mentioned earlier, the magnetization stays unsaturated, which may suggest that there actually might be more of the metamagnetic transition showing up at the higher field. And with that, that was our motivation to try even the higher magnetic field and go to the 73 Tesla duplex magnet. And here I would just like to show some of the curves collected at the low temperature, 1.4 Kelvin. So with the magnetic field applied along the A direction, we can see all the transition which were seen already, I showed already earlier. And indeed, we see one more, which is at 72.5 Tesla, which is literally at the limit of our duplex magnet, and it does saturate above that transition. Similarly, it looks when the magnetic field is parallel along the C direction, we do see a very huge jump at the 72 Tesla. It is followed by the saturation. When the magnetic field is applied along the B direction, we do see again one more transition at 62 Tesla. In that case, we do not see a clear saturation, but we definitely can say that the magnetization tends to saturate and probably will saturate shortly after our magnet limit. So with those data, when we are able to more or less collect the information about all the magnetic phases and that material, we wanted to look how it may influence the transport data conductivity, and if we will see any sign of the non-trivial topology. So we started from measuring the PDO, which is a radio frequency measurement of the conductivity. We can see here is the PDO coil, which on top we put the erbium manganese 16-6 crystal. That technique is sensitive to the changes in skin depth. Therefore, it will give us information about the changes in the conductivity when we talk about the metals or superconductors. The interesting part is that for some materials which are like semi-metals or insulator, it will be also sensitive to picking up the changes of the magnetic moment in that compound. And as we know, since erbium manganese 16-6 has a very complex magnetic structure, we might also see some influence of that. So this is the high field part of the PDO response, which I got. And with the magnetic field applied along the C direction, we indeed can see some quantum oscillation. However, when we move towards the A direction, we can see that around 40 degrees, the response of the PDO is dominated by the magnetic phases in that material. And when we slowly, I try to investigate further those quantum oscillation and take the background subtraction of this, starting right above those first metamagnetic transition, 27 Tesla, to pick up maybe even some lower frequency oscillation. And there is also just above the 45 Tesla to more focus on that high frequency oscillation part. This also clearly shows us that when we are around 40 to 45 degrees, the signal is very dominated by that sharp metamagnetic transition, and we are not able to see any of the quantum oscillation. So when I take the Fourier transform at 0 degrees, I can see two different frequency, one in the 120 Tesla and the higher at 775 Tesla. And by analyzing how does the frequency changes with angle, I was able to see that it is following a 1 over the cosine theta behavior, which suggests that this is 2D Fermi surface. And by creating the Landau-Venn diagrams and from the intercept extracting the value of the periphase, I was able to say that it has a non-trivial periphase. Now, comparing with the data which were already reported earlier, so in the magnetoresistivity, the low field magnetoresistivity data showed that the erbium compound, which is here the orange curve, has the frequency around 35 Tesla, which is much lower than what we are able to see. So that means that we are most likely probing some different different bands of the Fermi surface in that material. So in my summary, I just show again 3 different magnetization curves to show you how the variety of the magnetic phases and all the families, starting from the erbium manganese 16-6, which seems to be the more complex compound, the terbium one, which is the Ising ferromagnet, but we're able to define a new transition at 27 Tesla, and some complex low field magnetism, and the helium compound with the possible critical endpoint in that compound. Thank you.
All right, welcome back, everybody. Glad to see you all back after lunch. We're going to get started with the afternoon session. Our first speaker is Chen-Heng Du from Argonne National Lab. He's going to be telling us about synthesis and magnetoelectric transport properties of terbium manganese 6-10-6 thin films. So, Chen-Heng, please take it away.
Okay, thank you. Yeah, hello, everyone. Thank you for attending my presentation. Yeah, the topic of my presentation is the synthesis and magnetoelectric transport property of the terbium manganese 6-10-6 thin films. And we actually grow the film by we grow the film by cold deposition method, and first we grow several layers as the as
So I think I give my preference. So I would think that.
uh,
Right, so correct.
Huh?
So correct.
What?
So correct. Pronto, yeah, pronto.
Oh, sorry,
What do you
pardon
know?
me. I think some folks have a hot mic.
Great.
If you wouldn't mind muting yourself if you're not the speaker. Thank you very much.
oh, okay. Okay, so we first grow several layer as a state layer, and then we grow the connecting layer to make the film electric connecting. So the left panel, we can see the AFM image of a 40 unit cell thin film. The scale of the image is 5 micrometer. So from the AFM, we can see the film has a smooth surface, but it's not fully connected. And it actually is a island structure film. So the island will form the connecting the current path, which makes the film conducting. And the middle panel is the X-ray 2-theta scan. We can see I used the red label to label the peak from the substrate. We use the LSAT 111 substrate, so we can see only the peaks from the 111 direction. And I use the black labels are from the film peaks, so we can see the film are C-axis oriented. And we did a phi scan, influence phi scan to study the symmetry of the film. So first we use the LSAT 110 peaks as a reference. We can see the 110 peak of the LSAT of the LSAT, and then we use the 112 peaks of the film to study the symmetry. We can see a good 6-fold symmetry of the thin film. And also our high resolution TM data shows our film is in the correct phase of the terbium magnetic tin structure. When comparing with the single crystal, the film shows similar metallic behavior. But one thing different from the single crystal is above 30 Kelvin, the R versus T shows a nearly linear behavior. And when comparing with the single crystal, we have a like 1 order smaller triple R, which may come from we think come from the island structure of the film. So what is interesting in the film is the magnetic structure. When comparing with the single crystal, which implies maybe possible new order other than ferromagnetic order, as in the single crystal. We use 2 ways to probe the magnetic structure. One is the magnetization loop, and the other is the anomalous Hall loop. The magnetization curve shows multiple magnetic transition. Like here, the shoulder in the loop, which may come from different magnetic sublattice formed by terbium and manganese atoms. The saturated magnetization shows a decrease from the 2 Kelvin to about 100 Kelvin, and then increase from 100 to 300 a little bit. The hysteresis loop measured in the Hall and the magnetization are quite different. We compared it here. We can see at 300, the Hall and the magnetization loop seem to coincide with each other. But if we lower the temperature, we can see it's quite different. This is very hard to explain this difference by a simple ferro or ferrimagnetic order. So these are the summary of our magnetization and Hall measurement. Here is how the saturated magnetization changes with temperature. And here is the comparison of the coercivity we calculate from the Hall measurement and from the hysteresis loop. So although from the scale law we show here, our sample is not close to the quantum limit. But this whole assumption was based on a ferro or a ferromagnetic order in the single crystal. From our measurements, the thin film seems to have a different structure, a different magnetic structure. So we need more evidence to prove. So we have moved to the next step to check the possible magnetic structure in the thin film. And in order to check what really happened in the thin film, other than the hysteresis loop, we measured the zero field cooling Hall and magnetization curves at even higher fields. The Hall loops are the same for the 14 Tesla measurement are the same as the 19 Tesla measurement, 9 Tesla measurements. So if we look at the virgin Hall curves, we could have some interesting facts. The first is at low temperature, we see here the 2 and 10 Kelvin. It has no remnants at low fields, and then start to saturate, above the 7 Tesla. But if we increasing the temperature, they'll start to show a nominal Hall effect. The Hall effect could show the possible magnetic order of the manganese lattice as in the terbium manganese 16-6 thin film. The kagome lattice is formed by a manganese atom only. So the feature in the virgin Hall curves may come from the several possible reasons, like different magnetic structure, like maybe possible antiferromagnetic order in the manganese lattice, or the domain effect because of the island structure of the film, or maybe the manganese moment just fall into the hexagonal plane that's different from the C-axis. And we also checked the possible anisotropy of the magnetic moments in order to check if the manganese moment could possible to fall into the hexagonal plane. So we measure the autoplane, the in-plane magnetization of the film. Actually, the saturated magnetization indicates the moments are mostly along the C-axis at a low temperature. But there's a sudden jump below the 10 Kelvin. This we think comes from the terbium moments, which we can discuss later. And the difference from the Hall effects, which measure the manganese lattice only, the virgin magnetization curves could show magnetic properties both in the manganese and also the terbium sublattice. The left panel is the virgin magnetization curve to 7 Tesla. And if we enlarge it, we could see there is a bump here below 0.2 Kelvin. Before this bump, there is a sharp curve, and after it, the curve becomes flat. And the saturated is saturated slowly at higher fields. One conclusion we could have here is by zero field cooling, we could obtain a low magnetization state. Actually, this conclusion is confirmed by our XMCD measurements. For the XMCD measured as manganese ash, actually there is no contrast for the low temperature zero field cooling XMCD. That means there could be no net magnetization at the manganese lattice. And then we could have one hypothesis, that is instead of a ferromagnetic order, the two manganese spin moments may align anti-parallel, and then there is no net magnetization in the manganese sublattice. Also, the terbium could become paramagnetic order, which gives the rising tail in this saturated magnetization versus temperature curve. Actually, this is also confirmed by the flipping ratio in the terbium edge measurements. And the simple comparison of the version Hall and the magnetization curves as showed here. The left axis is the magnetization and the right axis is for the Hall. And the Hall measurement are measured up to 14 Tesla, and the magnetization are measured to 7 Tesla. As I said in the former slide, the Hall at the lower temperature here start to saturate to above 7 Tesla. But the magnetization is saturated at much lower fields. Although the former magnetic structure could partially explain this result, actually is still not fully understood by us, because the manganese oxidation state from our measurement is +2. So it's a little bit hard for us to understand, to fully understand what's happened there. So that means we still need more evidence to support our hypothesis in the magnetic structure. So in one in one word to summarize everything is that in the box single crystal, the magnetic structure of the moment kagome layers are ferromagnetic and ferromagnetic order. But in the film is still we are still not sure what really happened for the magnetic structure in our film. So one question is under what condition the antiferromagnetic structure could be favored over the ferromagnetic order. So we have some conclusions there. The first is from the growth side that the epitaxial thin film, we could get epitaxial thin film by cold deposition method, but the film itself is island structure. And at lower magnetic with the zero field cooling, we could get some low magnetization states. This means maybe possible antiferromagnetic order in the manganese sublattice. But we still need more evidence to support and exclude other possibilities. And thank you for your attention.
To our next presenter, Stephen Wilson, visiting us from Santa Barbara. So Stephen, if you don't mind sharing your slides, just make sure it all works.
Sure thing.
And just so you know, Stephen, we've been aiming for 20+10, but
okay.
Error bars.
I will hurt.
Telling us about the magnetic and charge order in the 166 class of topological kagome metals. So Stephen, please take it away.
All right, will do. Thank you. All right, great. Thank you very much for the introduction. And sorry, I got consumed with an advisory board meeting earlier today that just let out. So sorry, I'm just sort of parachuting in now, but I could stay around for the rest. Yeah, first of all, thanks for organizing this workshop. And I think this seems like it's a very diverse class of materials. It's 166 family of kagome metals, and I'm excited to kind of motivate and explain some of our recent work looking at sort of a vanadium-based class. So this are the rare earth vanadium 610-6 class in this materials family. So first off, just as an acknowledgement of the people who did the work. So Ganesh Pokharel has really been leading this effort in my group. He's been growing a lot of these materials and doing a lot of the bulk characterization and some of the scattering. And Zach Porter is a former graduate student in my group who's now at SLAC, who did a lot of the scattering work. I'll show you later on. And Farnaz Kabuvand and Sam Teicher did some of the DFT, or some of the kind of initial band structure modeling of some of these compounds. And we've also had the good fortune to collaborate with a number of great sort of complementary probes. So for STM measurements, we've worked with Ilya Zeltovich's group at Boston College with theoretical guidance by Zikang Wang. And photo emission, we worked with Junfeng He's group, as well as Federico Mazzola's group. And our X-ray measurements that I'll be showing you later on were performed primarily at Chess, but our resonant X-ray measurements were performed at Argonne with Zahir Islam, Phil Ryan. And yeah, we'll go from there. Okay, great. So you guys have probably seen this a million times, so I won't belabor this. Just of course, the kind of broad motivation of kagome metals is that you can realize sort of this interesting coexistence of Dirac points, Van Hoff singularities, and flat band features. So depending on where you are in terms of band filling, you can access some various subset of these, and hopefully maybe some coexistence of correlated electronic phase behavior, and also maybe topologically non-trivial band structures. So there's a wide variety of systems which can sort of access some of these various features. So for instance, iron tin or sort of these manganese-based 166 compounds kind of exploit a lot of the phenomenology that comes from gapping out the Dirac points sort of that arise that are native from the kagome band structure. So Joe Chukelski's group's got some beautiful recent work on nickel-3 indium, looking at flat band physics. For instance, if you can tune the Fermi level towards the flat band in the kagome band structure. And so these vanadium-based 166 compounds I was showing you, they nominally have fillings which are near the saddle points in their Fermi level. So this is kind of spurred some of our initial interest in these materials. And so I'll just try and talk about two key classes. The first would be sort of understanding which types of magnetic order can be realized in these systems. And the second class is looking at an instance of charge order that's realized in these materials. So first off, just a quick overview of the structure. You guys are all familiar with this. So basically, as we know, these are just basically a kind of ideal kagome nets, and in this case, vanadium ions, which are non-magnetic in these materials. And so this forms this bilayer structure. And in between these bilayers, you form a triangular lattice of rare earth ions. And so the idea then is that you can try and realize or manipulate sort of filling control in the non-magnetic kagome net, and then sort of interface that with a variety of different magnetic states that are realized in the triangular lattice network of rare earth ions. And so, in an ideal scenario, you have sort of independent control of the two, perhaps. And so if you look at the band structure, let's look at the non-magnetic version. So yttrium, vanadium 6-10-6, this is just from DFT, showing the contributions of the Fermi level, which predominantly come from the vanadium ions in the kagome net. You can see that the filling is rather close to some of these Van Hoff singularities near the M point. And there's also, the filling is also close towards sort of this K point Dirac crossing in these systems. And then there was some discussion I see in the previous talk about sort of DFT plus DMFT type band structure calculations for the manganese variants. And so it's not, dramatically different, but this is sort of the vanadium system is non-magnetic, so perhaps it makes life a bit easier. Okay. So another sort of flavor, kind of wrinkle is that the surface state's predicted to be close to the Fermi level in these systems. They're technically sort of Z2 topological metals. So one can sort of do the standard sort of band structure classification of these systems. And there's some hint that some of these topological surface states may be there from photo emission measurements by Jungfeng He's group. But there are also a number of trivial surface states that come from the tin states also in this material. And there's been a lot of work trying to probe a substantial spin-Berry curvature in this class of materials. So this is some photo emission work done by Federico Mazzola's group, where they're doing sort of spin-resolved ARPEs, but using circular dichroism, circularly polarized light. And from that, basically, they can resolve sort of at the gamma point. They're seeing this sort of large signatures of Berry curvature, of spin-Berry curvature in the material, which gives rise or contributes to the sort of anomalous Hall effect in these compounds. And then they did it for the terbium system, but the sort of qualitatively similar behavior is observed for the scandium, which is another non-magnetic system, as well as homium. So it seems to be kind of a generic feature. And these are all done in the non-magnetic state of all the compounds. Okay, so what we wanted to try and do when looking at these systems is try and understand to what degree we can manipulate magnetic order in these compounds. And so, I guess, so the typical game with rare earth ions is to try and just tune the lanthanide ion judiciously. So first off, starting with non-magnetic, so basically yttrium, vanadium 6-10-6. Okay, so indeed, if you just look at the susceptibility of this system, it's indeed non-magnetic. The vanadium ion doesn't carry any local moment, so it's more or less a polyparamagnet with some very weak upturn at low temperature due to some dilute fraction of paramagnetic impurities. If you look at these compounds, you can parameterize sort of the Hall basically the Hall response via a via a two-band model, and they're basically it's a multi-band. It's a two-band model, and it's reasonably high mobility metals. And this picture more or less holds for all of the variants I'll be showing you. But what we can do then is we can then take the yttrium ion out and we can replace it with a magnetic ion. And the first one we chose is one that you typically expect to add some strong anisotropy to the system. So we put terbium. So it's a terbium vanadium 6 tin 6. And so the magnetic order that's realized in this system is if you look at low temperature, so this is in the ordered state, you can see it's a strong easy axis anisotropy with the moments pointing along the z-axis. So that's sort of out of the Kagome plane. And you can see basically here, you can see the effect of the moment pointing along the field pointing along C and a very strong anisotropy versus when you put the field in the AB plane. Okay. And so you can start to see hints of this in the magnetization, but sort of there's a low-lying crystal field sort of out of this doublet ground state into, so it's a, basically the terbium 3+ is a J is equal to 6 multiplet. And so the first excited state, you can start to see hints of that being populated when you warm near 50 Kelvin. You can look at it a bit more in detail if you just look at the heat capacity and just fit it to sort of this two-level Schottky anomaly. And so basically the first excited state is around 10 millivolts. And you can also use the heat capacity. You can see the sort of the strong, you can see the onset of ferromagnetic order at about 4.3 Kelvin. So, okay, so the picture for the terbium vanadium 6 tin 6 system is that, okay, then you can take this Kagome band structure and then you can interface it with a C-axis aligned ferromagnetic state with a strong sort of uniaxial anisotropy. Okay, so then we can look at the sort of opposite extreme, and we can replace terbium with gadolinium. And when you do that, so basically we should be looking at a much more sort of isotropic ion, the gadolinium 3+. If you look at the susceptibility as a function of temperature, and as you cool down, you can see sort of in the low field limit under 10 millitesla, you can kind of see there's kind of a downturn and maybe some subtle structure in the susceptibility as you field cool the system. If you were to apply magnetization in the ordered state, either with the field in the orthogonal to the Kagome planes or within the Kagome planes, you can see that the response is pretty isotropic as you would expect. But then if you look at sort of a magnetoentropy map using just the Maxwell relations from susceptibility data, then one can see that there's some type of feature here at low temperature in the ordered state around 0.2 Tesla. It's sort of an entropy anomaly. And this is usually kind of you see this in a lot of non-collinear ground state systems where in the low field state, you have sort of a non-collinear state that gets easily polarized. And so there seems to be some feature that's quenched under about 150 millitesla in this magnetoentropy map. So we wanted to try and understand what the zero field ground state is. So to do that, we first, okay, I'm going to show you some resonant X-ray scattering data exploring that. But kind of just digging in a bit more, if you just kind of zoom in at the low temperature susceptibility as a function of temperature, you can kind of see there's sort of two features, something around 5 Kelvin and something a little below 4 Kelvin in both the susceptibility and potentially in the heat capacity here, kind of hinting that there's maybe some staging of the order from these two probes. And indeed there is. So if you look at if you do resonant X-ray scattering measurements in this system and you basically tune to the gadolinium L2 edge, what you can do is basically, you can cool into the ordered state. This is, again, this is at 6 IdB at the advanced photon source. What you can find is that along the C-axis, along the OOL direction here, you can see that there's incommensurate magnetic peaks that turn on when you cool below 5 Kelvin. When you cool below 5.2 Kelvin. And you can see these peaks as you continue cooling kind of slide in, so they sort of evolve a bit. In the lowest temperature, you can see there's sort of an additional peak that appears at the sort of half integer position. And if you look at the sort of a map of intensity as a function of temperature, you can see these incommensurate peaks kind of the Q vector evolving, kind of initially kind of expanding outward and then coming back in as you cool down towards the ground state. And then as right at this sort of bend or this inflection, you can see the onset of this weak commensurate harmonic appearing at the 0.5 position. And so if you could look at the intensities of these two, order parameters as you cool through the ordered state. You can see first there's this onset of incommensurate order with kind of a sliding Q associated with it. And then at low temperature, at this sort of second sort of stage transition, you see this sort of commensurate harmonic turning on. Okay. So to summarize sort of the tunable order that can be realized then, if you're looking at these sort of two extremes, the first is, if you put terbium in there, we know we can interface the kagome net with sort of a strong uniaxial ferromagnet. And then if you kind of go to the opposite, more isotropic limit with gadolinium 3+, then we realize an incommensurate antiferromagnetic state. In this sort of incommensurate modulation, right now, our best models are, that's basically a moment modulated state that's likely driven via nesting of small pockets along the c-axis via RKKY exchange. But there's more experiments that need to be done to really validate this type of model. Okay. And then, in between, I think there are some reports of by other groups of erbium and thulium, I believe, that's like an easy plane anisotropy and antiferromagnetic ground state. Okay. So it's kind of switching briefly to discuss charge orders. So in the yttrium vanadium 6-10-6 system, as I showed you, it's just sort of a non-magnetic system. It also doesn't realize any electronic instabilities that we can tell. But so David Mandris's group showed that if you put scandium in place of yttrium, then below about 100 Kelvin in the susceptibility, resistivity, and heat capacity, you can see that there's a phase transition that occurs that's consistent with the onset of charge order. And indeed, when you look at the structure of this system, as you cool below this transition, there's basically a √3 by √3 by 3 enlargement of the unit cell with a wave vector of a third, a third, a third. Okay. And so what's happening here is if you think about from first principles, this is from calculations by Binghai Yan's group. If the structure is unstable, it's unstable to distortion, but actually the most energetically favored distortion is a √3 by √3 by 2. So basically the unit cell enlarges in plane √3 by √3. This is consistent with the experiment, but only doubles along the c-axis. Whereas this is the experimentally observed distortion. And you can see it kind of sits in a rather like maybe shallow minima. There's several different types of distortions that may be close in energy, but sort of the DFT predicted dominant instability is this √3 by √3 by 2. Okay. And so one way of thinking about what's going on, the primary kind of actors in this lattice instability are the tin and scandium ions. And so if you look along the c-axis of this system, you can see here there are these sort of units of scandium and tin that kind of slide up and down the c-axis in a modulated way. And so one way of thinking about that is thinking about the importance of these. One way of thinking about it are these chains of scandium and tin along the c-axis. And so if you kind of just decompose the 1-1 or iron tin structure, if vanadium tin was a thing, you could envision it like this. And then I can basically, if I think about this tin-2 site, this forms a honeycomb network in this plane. And in the centers of those honeycomb sites, you could put the rare earth ion, okay, when you start to make a 1,6,6 compound. And that'll displace the tin atoms above and below out of the kagome network where the vanadium ions sit. And so since you've then created this like squeeze space and the layer up immediately above or below it, you end up with a bilayer structure, okay? It's because you can only put one for every two, you can only put one layer of rare earth ion for every 2 vanadium planes. And so what you end up with is this 1,6,6 structure. So really sort of the defining trait, of how you squeeze these in are these chains and this motion of these tin atoms relative to the rare earth sites. Okay. So then one can imagine what happens. So when you think about the structure of the yttrium vanadium 6-10-6 system, and you look along these c-axis chains, okay, and these chains, these tin atoms are being displaced out of the kagome net, right? So these chains thread through the centers of the hexagons in the kagome lattice, okay? And so in the yttrium vanadium 6-10-6 system, the spacing along the c-axis between these ions is about a third of a lattice constant along the c-axis, okay? So then what happens is if you replace yttrium with scandium, you put a much smaller atom in there, and that basically activates an instability, and it allows these sort of tin atoms that were displaced to kind of move in closer to the scandium site. So you can end up then with a modulation of, let's call these sort of like trimer units, where you have a short, or you basically end up with a modulation along this chain of short and long bonds. And so you end up with these sort of decomposition of this kind of equally spaced chain into these sort of maybe trimer units that can move together. So if I think about this sort of trimer unit along the c-axis, and I just go one coordination level out, and I just think about these are the vanadium ions where these guys slide, move around. When these tin atoms try and move into the vanadium plane, okay, they basically displace the vanadium ions out, and there's some steric penalty associated with that. Okay, so fine. So if I kind of build out one more level in terms of the in-plane structure, then you have these chains going through the centers of these hexagons. And ideally, since there's a steric penalty for moving one tin atom into the vanadium plane, you don't want to put two trimers moving in the same direction next to each other. Okay, so then you can imagine I have like a triangular lattice then, where I have to try and decorate one trimer moving up next to one trimer moving down. Okay, so what you end up with is sort of a frustrated lattice in this regard. And so one way the system can solve this is to basically just to unlock an additional degree of freedom along the chain and just say, okay, well, one trimer moves up, one moves down, and one doesn't move at all. Okay, and so then you sort of have an ABC tiling of this triangular lattice. Okay, so why is this significant? It implies that the structure that DFT predicts, this root 3 by root 3 by 2 structure, could potentially be somewhat frustrated, okay, in terms of forming long-range order, and that long-range order can't form until you can kind of realize this longer wavelength modulated structure, which is experimentally realized, which is this root 3 by root 3 by 3 structure. Okay, so experimentally, indeed, that's what I'm going to try and motivate is this is what's happening. So if you look at high temperature, okay, so again, the charge order transition is at around 90 Kelvin in this system. But at high temperature, this is in the third a half plane. So this is the wave vector corresponding to the DFT predicted root 3 by 2 structure. You can see there are these diffuse charge correlations that grow and then strengthen and then reach sort of a maximum intensity right at the onset of charge order. And then they sort of dampen as you cool below that. Okay, so these are short range correlations at sort of the DFT predicted structure, which is also naively potentially a frustrated lattice. Okay, and if you look at the plane in which you can see correlations associated with the root 3 by 3 structure, you see these sharp long range peaks, and these guys turn on in a first order like fashion. So if I look at the trade-off between the diffuse scattering intensity at the third a half plane versus the diffuse scattering at a third, you can see that basically the correlations are present at high temperature. They increase slightly in intensity, and then once the long range order turns on, basically you see a rapid suppression in the third a half wave vector. Moreover, you can look at the correlation length. So if you look at the correlation length of these third a half correlations along the c-axis, that you can see they kind of more or less remain flat. They start diverging. You hit around 3 unit cells correlation along the c-axis, and then you can see, boom, the onset of long-range charge order at the third a third type position occurs. So you can test this a little bit more by just saying, just doing some substitution. You can say, okay, I'm going to replace a little bit of the scandium, which is this, now I have this much smaller site with a larger yttrium ion. So when you do that and you look at susceptibility as a function of doping yttrium onto the scandium site, you can see that the parent charge order, which is around 90 Kelvin or so, is sort of rapidly suppressed. And maybe that suggests that you have sort of a dominant one-dimensional instability that's sort of whose coherence is easily interrupted via this substitutional disorder. And you can also then just examine it a bit more carefully and say, what do the short range correlations look like? And what we find is that by the time you put 3% yttrium into it, you've completely disrupted the long range order that we can see via X-ray scattering. And instead, you just have these remnant third a third by 2 type of correlations in short range order. And by the time you put 8% yttrium into it, basically all charge correlations vanish. Okay, so you have this really rapid suppression of this charge instability in this compound via just sort of steric effects, or just a site substitution, isovalent substitution. And I just want to highlight this is a similar a similar experimental picture has been shown by some by similar also very nice X-ray diffuse scattering measurements by Santi Blanco, as well as some nice work by Yusong. And I'll also say that sort of transport signatures of sort of these high temperature correlations have also been seen by Junhao Chu's group at University of Washington. The impurity substitution, similar work's also been recently published by David Manders' group, and there's been what I presented was more of a heuristic model, but there's some very beautiful microscopic theory of what's going on, which I kind of highlight here. Okay, so just to conclude, I'll just say, just motivate that, in general, I think we're all here because we think kagome metals are sort of interesting platforms for looking for new electronic states due to their interplay between correlation effects and non-trivial topology. The 166 class, of course, is very versatile. We think the vanadium-based class is an interesting one because you can kind of tune a non-magnetic kagome net relative to a triangular lattice of rare earth ions. And, sort of our initial work shows that you can realize the diversity of magnetic states. And sort of the scandium 166 compound is sort of a unique kind of member of this class of compounds because it sort of realizes what seems to be sort of a frustrated charge order at high temperature. And with that, I'll thank you very much for your attention.
Okay. Hello, everybody. I'm William Meyer. I'm at UT working with David Manders. I took an opportunity today, so I would ask for some forgiveness if there's errors on these slides. They've been put together in about an hour. So, but Stephen's talk, actually, I can build upon it a little bit, and we were kind of co-developing our ideas. And
William, I'm sorry, just can you maybe just can you make it full screen, the slides?
Yeah. How about that?
That looks great.
Okay. So what I want to talk a little bit about is kind of a chemistry model for why the charge density wave can develop in scandium, vanadium, tin, but not lutetium or yttrium. And that was kind of motivated us to do a detailed doping study, not just of scandium for yttrium, but scandium for lutetium as well. So I'm going to introduce the charge density wave that Stephen has already discussed. I'll talk about what happens when we dope with lutetium and yttrium. And then I'm going to talk about a rattling chains model that I came up with to kind of describe this. And that has some interesting implications when we ask our chemical and physical pressure equivalent. Then I'll summarize on that. So the charge density wave in scandium, vanadium, tin is different than that in the other vanadium compound, kagome compounds so far. So when we made crystals of scandium, vanadium, tin, Hashitha noticed that there was a drop in the electrical resistance at around 94 Kelvin. Magnetization measurements also showed a drop, although it's just a paramagnetic metal. So we're not looking at like an antiferromagnetic transition. It's first order. And strangely, as I mentioned, there's both a drop in the susceptibility and the resistivity, and that's odd. Most charge density waves see a jump up in resistance as a gap opens. So something's a little different here. The explanation, it turns out, is we do have fewer carriers, but they're just scattered less. And that decreased scattering leads to a drop in resistance. So single crystal X-ray diffraction. At room temperature, we see our nice rectangular array of peaks. And at low temperatures, we see this new charge density wave develop with a 1/3, 1/3, 1/3 wave vector. You can see these new rows of peaks appearing. This 1/3, 1/3, 1/3 has been quite a lot of fun. It turns out that's not what DFT would initially predict until you start really digging into the details. We also have neutron diffraction confirming that this really does develop at the transition observed in transport and thermodynamic properties. The nature of this charge density wave is also different than the cesium, vanadium, antimony family materials. It's a different unit cell. It enlarges our unit cell in the AB plane. I want you mostly to ignore how these red vanadium atoms move. They move very little, but it does increase by a factor of 3 in the AB plane. Along the C-axis, we get a doubling of 3 as well. And as Stephen pointed out, these vanadium and tin atoms are moving the most, and they're mainly moving along the C-axis. The vanadium atoms are kind of spectators here. And they move a big distance. 1.7% of the unit cell is a lot. And we have this periodicity. And I really like what Stephen was pointing out about the triomers. Until I read their paper, I really didn't appreciate that these 3 atoms here, one moment, please, are moving together. Their displacements are the same. So that each one of those forms a little rigid unit. And these tin-1 bonds, I'll introduce that a little more in a moment, change either closer or farther together. So let's talk about how we set out to tune the charge density wave. Not long after we reported it, a group in China, applied pressure and noticed the charge density wave was suppressed. I don't think they ever found superconductivity, but clearly squeezing this unit cell suppresses our charge density wave. And now we look at the other members of this family. Scandium, lutetium, and yttrium are all 3+ cations. So wouldn't we expect them to do the same things electronically? But when we do magnetization, we see that the 3 of them, a charge density wave only appears in the scandium compound. So why is that? Well, we actually have a really nice situation here. We can independently address whether it's the size, mass, or the lattice that's really making the difference here. It turns out if you look at scandium, lutetium, and yttrium in size, the order goes scandium, lutetium, yttrium, getting bigger. And in mass, it goes scandium, yttrium, lutetium. That means that we can independently see which one matters more, and we can monitor our lattice parameters to see what matters. So when we go between these compounds, doping with lutetium, we notice that our charge density wave, our drop in resistance here on the black curve, drops in temperature as we dope in our magnetic susceptibility measurements. And we see the same thing as we dope with yttrium. So both of these rapidly suppress that charge density wave. In fact, we're talking by 15% doping, the charge density wave is gone. Now, oh, I have written this wrong. Yttrium fills that charge density wave faster than lutetium. I'm sorry. You can see that here, that this point here, our charge density wave is gone by 9%, where it lasts until at least 12% in the lutetium data set. So here's an interesting thing. So if we simply take the radius of the average radius of the rare earth ion, I realize using ionic radius on a metal is imperfect, but I don't have a better way. But if I plot it like that, you can see that the slope of charge density wave versus average radius matches for the 2 data sets. So size appears to be more important. Doping with yttrium kills that faster. If it was the other way around, if lutetium killed the charge density wave faster, it would suggest that that heavy lutetium atom was more important. And that would be kind of counterintuitive anyway. Scandium's the lightweight atom. It should have the highest energy phonons. So size matters here. That tiny scandium atom is what's allowing the charge density wave to form. And there's more evidence for this. So let's take a look at our lattice parameters for our rare earths, for our series and our other rare earth compounds. So on the right here, I show our C lattice parameter and our A lattice parameter for the whole family of rare earth vanadium tin compounds. And there's duplicates in there because I was trying to include as many data points as possible. Here's lutetium, yttrium, and scandium sits off to the side. That's already interesting. But once we look at our doping series, our small data points here, you can see that putting the bigger lutetium atom in just increases A. C is almost constant. And if you look at the C lattice parameter, slowly increases. Clearly, these big rare earth atoms, the big or I guess they're not lanthanides, but the bigger rare earth atoms aren't increasing the C lattice parameter as much as you'd expect based on their size. So what's accommodating those larger rare earth atoms? Well, I argue that if we're putting a bigger rare earth atom in, we got to move the tin along the C axis away. So if we look at our stack of rare earth and tin atoms along the C axis, these are in the channels of the kagome network. This distance here between tin 1 and the rare earth is going to grow as we put a bigger rare earth atom in. And you see that bigger rare earth atom radius, bigger distance between them. But because our C lattice parameter doesn't move as we put bigger rare earths in, the tin-tin bond distance has to decrease. And we see that in our single crystal diffraction data. The tin-tin bond is already squishy. That's critical. We can see that because as we put those bigger atoms in, those bonds get closer. And that squishiness means that there's room in this column atoms for displacements. And we see those displacements. They show up in the diffuse X-ray scattering that Stephen and other groups have presented. And we see it in diffraction even at room temperature. So on the right here, I show the 95% displacement ellipsoids for scandium, lutetium, and yttrium, vanadium tin. You can see that they're all a little bit cigar-shaped, but the scandium, in the scandium compound, they're significantly larger. They're almost twice the displacement parameters of the lutetium and yttrium compounds. These atoms are wiggling wildly, even at 3 times the charge density wave temperature. So clearly, there's a rattling, these atoms are rattling around when this titanium or then the scandium atom is present. And you can see that's much less with the lutetium and yttrium. So let's revisit our chemical structure. We've seen this a number of times today, but I'm going to want you to think about it a little differently. Instead of a bilayer, I want you to focus on the vanadium atoms and these tin-2 and tin-2 and tin-3 atoms that form honeycomb sheets. And think of them as a rigid stack of layers. And if you think of that, then you see that there's a channel in the kagome and honeycomb network here where our rare earth and tin atoms sit. So this rare earth tin-tin chain fills these channels in the structure. Now, we've already shown that when we, in the scandium atom, those atoms are rattling up and down quite a lot because this stack is rigid and they're loosely filling it. If we can remove that space by squeezing the crystal lattice, compressing that stack, or putting a bigger rare earth atom in and taking up that extra space, we can remove that charge density wave instability. And that's what we see. Pressure kills the charge density wave. Doping with bigger rare earths kills the charge density wave. But something's odd here. Generally, when we put a bigger atom in, we're thinking of negative chemical pressure. We're expanding the lattice. And when we squeeze, that's positive chemical pressure when we apply gigapascals of pressure. So something's odd here. But our rattling chain model suggests that they should have different effects. We're using the bigger atom to fill up that volume, and we're using the pressure to squeeze the network around it. So what you can see here is our family of rare earths on our C versus A plot and our scandium. And the negative chemical pressure by doping pushes our, either expands or fills up that channel without changing the C lattice parameter. And physical pressure compresses the lattice. So this makes a prediction. These two should conspire. We should not, if we take a doped scandium vanadium tin sample where the charge density wave is suppressed, we expect that charge density wave to be further suppressed with pressure, not increase again as we shrink the lattice. And that's exactly what we see. So if I start with a lutetium doped scandium vanadium tin sample, where my charge density wave is order 60, 65 Kelvin, applying pressure does kill the charge density wave. That means that they're conspiring together. Negative chemical pressure and positive physical pressure are working together to kill the charge density wave. This means that chemical and physical pressure are not exactly equivalent in this model. And that's kind of neat. So with that, oh, I still have an error. I want to tell you that scandium vanadium tin is special in this vanadium 166 family. It's the only one that appears to have a charge density wave. And if we dope it with yttrium, we see that that charge density wave disappears faster than with lutetium. And that suggests that that rare earth size is key. And we notice from our diffraction measurements that the tin-tin bonds are accommodating that larger atom. And we're squeezing out that extra space between those tin atoms that allowed our charge density wave to develop. That means that the tiny scandium atom is the reason that scandium vanadium tin is special. It leaves room for those atoms to rattle in those channels. And then it also allows room for the displacements of the charge density wave mode. And this leads to an unexpected story where chemical and physical pressure don't have the same effect. So thank you for the opportunity to give that impromptu overview of our work. And I think it actually meshes really nicely with the stuff that Stephen's group has been doing. So with that, I'll take a few questions.
Okay, so this is Rob again, and I'm going to be chairing this last session for the workshop. We have 3 more scheduled talks. The first one is given by Ben Yulin from Ames Lab. Title of the talk is Rare Earth 166, Kagome Layers, Interlayer Competition and Topological Implications. So Ben, take it away.
Sure. Just give me a second. Okay. So thanks, Rob, for giving me the opportunity to present our work. So yeah, as Rob said, I work with him at Ames Lab and Iowa State University. So we've been working on this project now, this 166 project, probably since 2020. So today I'm just going to go over some of our results for terbium manganese 6 tin 6 and a little bit of erbium manganese 6 tin 6. And then I'll just talk here or say here also thank you to the Department of Energy, Basic Energy Sciences for funding our work. Okay, maybe this will work. There we go. Okay, so we've had a lot of collaborators over the years. Of course, we have our neutron scattering collaborators we usually go to at Oak Ridge and at the University of Missouri. These samples that we measured largely came from Paul Canfield and Tyler Slade here at Ames. And then you've heard already from Lee Chin today. We have great theory support from Lee Chin, Young Bin, and well, Peter Orth has moved on to a position over in Germany now. Our high magnetic field work, we have collaborations going on with Ross and his group. And then also we have a great set of students and postdocs at Ames that have helped us a lot with this work. Okay, so let's see, tunable magnetism and rare earth manganese 6 tin 6. So we've seen this a lot. The interesting thing about kagome metals is that you naturally get these Dirac crossings at the K points and flat bands. The trick is getting these interesting features in a real material near the Fermi surface so that you can actually observe something. So a lot of these materials, a lot of the heavy rare earths order in a ferrimagnetic structure. So you have the manganese, so the kagome layers are always ferromagnetically aligned. I should say each layer, the rare earth and the kagome layers are ferromagnetically aligned, but the orientation between the rare earth and the manganese kagome layers is anti-ferromagnetic. So you have a ferrimagnetic structure, but you still get this net overall magnetization. And depending on the rare earth that you use, you get different anisotropies, and a lot of this depends on the crystal field splitting of the rare earth, as Lee Chin talked about earlier. So as I said, a lot of these heavy ones, you get ferrimagnetism. with the rare earth anisotropy controls. But then also on the other side, so if you go to non-magnetic yttrium and even for erbium, as I'll show you, you get competing manganese and manganese interactions, competing interactions between the layers, which can lead to helical magnetism. And then depending on the conditions, you can observe a topological Hall effect. Okay, so that's kind of what drove us into real interest in these materials. So if you look at the left side here, this is an old graph from Malaman back in 1999. And you can actually see, so this is for the ferrimagnetic state, ferrimagnetic ground state, the angle away from the C-axis with decreasing temperature, right? So if we look at the terbium, for example, we see at high temperature, right? So all these materials seem to order above 400 Kelvin. The rare earth and the manganese seem to order at the same time. So as you cool down, so here it's easy plane, so it's driven by the manganese easy plane anisotropy, but then as you cool down, the uniaxial rare earth anisotropy takes over for the terbium, and you get the overall ferrimagnetic structure now aligned along C. For holmium and dysprosium, you see the same thing. You see the spin reorientation transition. You don't end up in the C state. You end up slightly canted away from it. And then erbium, I'll talk about later in the talk. This is actually a little misleading here about the erbium. Not that we don't have a spin reorientation transition, but just that the erbium is not always ferrimagnetically ordered. And then the gadolinium, of course, remains easy plane. So you also have these H-driven, so these field-driven spin reorientation transitions. So you can drive for H parallel to C here for the erbium. So the erbium at low temperature is in an easy plane ferrimagnetic state. You apply a field along C, you can get this metamagnetic transition. As you exit out of the ferrimagnetic state into what I'll show you later is the spiral state. You lose this step and you start getting this linear type behavior before you get this rollover to a plateau. So let's see. So we have the ferrimagnetic to helical order and erbium 166, which I'll talk about before. And then of course, we also have the helical order and yttrium 166. And these are neutron diffraction patterns showing that. All right, so the results I'm mainly going to talk about here are from inelastic neutron scattering and neutron diffraction. We have two main modes to do this, right? We use either a time of flight spectrometer, where you have neutrons that are created by a proton pulse hitting a target. The pulse is, a bunch of neutrons centered around a certain wavelength. They're selected by a velocity selector. They go in, they hit the sample, and then they scatter into this large detector array. For these type of experiments, especially for magnetic inelastic neutron scattering, you need a lot of scatterers because the scattering is so weak. So we typically co-align single crystals into these large arrays, usually just using an in-house X-ray Lowry system. The triple axis we use more nowadays for diffraction because you can get very good signal to noise and you can focus in on specific Bragg peaks and look at order parameters. So for the triple axis, you just basically select an incoming energy using a monochromator. You hit that on the sample, it scatters off the sample or diffracts off the sample, and then you select the final energy you want to look at using an analyzer, and you can set this up to look at different modes of energy transfer and momentum transfer. So the great thing about neutron scattering, especially magnetic neutron scattering, is you get this overall 4D view of chi, double prime, Q, and omega, right? So the scattering intensity is just related to the imaginary part of the magnetic susceptibility for magnetic scattering. All right, so getting back to the R166s. So for our diffraction and inelastic scattering measurements, we've been using this Heisenberg Hamiltonian in a mean field approximation mainly, but right here we get the Heisenberg Hamiltonian. The main interactions are you have the intra-layer manganese exchange, which is strongly ferromagnetic. So like I said, layers here are all ferromagnetically aligned, and you get this antiferromagnetic coupling between layers. So here I've got the low temperature terbium manganese 6 tin 6 state shown. So the first interlayer interaction, the one we call J1, is between two manganese layers, so J1MM. That goes across a terbium layer. And then we have these manganese bilayers also, where there's no rare earth in between them, and we call this J2MM. And then it turns out, well, you also need this interaction between the rare earth and the manganese, of course. But then it also turns out that this J3 interaction, which goes across all these layers I'm showing here, this actually turns out to be very important in that it competes with J1. So as I said before, so J, the intraplane interaction for the manganese is strongly ferromagnetic. Turns out J2 is ferromagnetic. Of course, this rare earth manganese interaction turns out to want to be anti-ferromagnetic. Give you your it turns out to be wants to be anti-ferromagnetic, and then you have this competing J1, J3, and depending on the relative signs of J1 and J3, you get differences in the magnon spectrum, which you can detect readily using our inelastic neutron scattering. All right, so we have the easy plane manganese anisotropy, of course, also within this Hamiltonian we're building. And then you have the complex rare earth anisotropy that depends on the crystal field splitting. Okay, so from that Hamiltonian we just built up, we can look at what we would expect in the magnon dispersion based on the Hamiltonian. So for the kagome layers, you get these nicely dispersing bands here because they're bilayers. So you have that bilayer splitting. Because they're bilayers, you actually get a splitting of these bands into what we call even and odd modes, and they're called even and odd depending on what gamma point you actually see them at. And you'll see that in the next slides. So these manganese magnon bands, they feature these Dirac points here at the K course at momentum transfers corresponding to the K point for the kagome layers. And then also you expect to see these flat magnon bands up at much higher energy. And we predict this energy scale to be up near hundreds of millivolts. Okay. So let's see, the center panel here again shows the splitting between the even and odd bands. And then it also shows where you expect to get bands due to the rare earth atoms. So in this case, terbium. Right, so let's see, so you get even these odd and even branches due to the bilayer coupling, which is set by this energy scale here. The strong anti-ferromagnetic interaction between the manganese and the rare earth gives an exchange field with a scale of JMT, but modified by the difference in the overall moment here. And then, excuse me, the rare earth anisotropy here gives the even magnon branch a spin gap on the order of the square root of JMT times KT. Okay. So sorry, I kind of swallowed a frog over the weekend, so I'm a little rough here. Okay. So competing interactions in terbium 166. So these are some of our inelastic neutron scattering data that we took on ARCs using the sweep mode. And you can see we get these very nice pictures of the even manganese modes coming down here. We're showing across the minus K, 2K4. So you see this manganese mode come down. You get the gap right at 004. And then we have the odd mode here, looking around 003, you can see the minimum in the odd mode. And these pink lines here correspond to fits to that Hamiltonian we built up prior. And then in the mid-range here, so these manganese modes, they extend up to high energy. In the mid-range here, just below 30 MeV, you have this terbium mode, which is slightly dispersive across the zone. Looking at another cut here, you can clearly see the gap between, so this is along the OOL direction, you can clearly see the gap between the even and odd branches, and then you see the terbium branch lying in between. So our fits basically confirmed that we have this uniaxial terbium anisotropy. So I should say all these data were taken at 6 Kelvin. So this is the low temperature state where the ferromagnetic order is along the C-axis. J2 is strongly ferromagnetic. We have the easy plane manganese anisotropy. We find though that J1 is ferromagnetic and J3 is anti-ferromagnetic, and that gives us basically where these odd and even branches sit here, and these patterns of what energies they sit at. And then J1 over J3 is about equal to -2, which indicates some frustration. And so what's important is we found that these interactions can be transferable. What we found, it's also been shown that the interactions that we solve for here can be transferable across the series for a number of these rare earths. All right. So I might start going a little quicker here. So we have the spin, we looked at the spin reorientation transition to see what happens as we heat up. So if we start, so if you look at the top right here at 100 Kelvin, you see this upper terbium mode here, again, centered around 25 mil MeV in this case. As you heat up, you start seeing the development of a mode down kind of in with the manganese mode here, and that corresponds to this lower terbium mode that starts coming in. So you see the disappearance of the upper one, you see this lower one coming in. They both coexist over a certain temperature range, and then once you get to the spin reorientation transition, the coexistence disappears and you're just left with this lower terbium mode. Rob was able to recreate this behavior doing some RPA calculations, and this was I know the developing the RPA was in conjunction with Chris Stock's group and Stephen Wilson's group. And he was able to recreate how this, the spectra pretty well, including the spin reorientation transition. One thing that is noticeable is that the RPA does predict a lot more modes that are not seen in the data. Right. So this upper terbium mode now, we know is associated with the uniaxial terbium anisotropy. Again, this is just another slice looking along a different direction. You come down, you see the coexistence of the two modes, and this coexistence actually of the two modes actually corresponds to the coexistence of two states, this uniaxial ground state that we have and an excited state that's more isotropic. And then once you get past the spin reorientation transition, all that you're left with is this isotropic lower terbium mode here. And you get the ferromagnetic state following the manganese easy plane anisotropy, where the manganese and the terbium both lay in the plane. So on the right side here, I just show some more details of the crystal field states. Basically, the molecular field, of course, is going to also split the terbium crystal field states. And then this nice graph here shows how you, when warming up, you get this coexistence of the uniaxial and the excited isotropic states. And then once you're above the spin reorientation transition, all that remains is the isotropic. And we have some proof of that that's discussed in the paper here. So in this intermediate regime, it's an interesting regime that Rob has come up with this interesting name of calling it a binary orbital quantum alloy, where you can map this coexistence into what you would expect if you had some kind of mixed alloy. And you can show using some classical Monte Carlo simulations that you get this, you would expect the same kind of structure, the same kind of scattering pattern. Okay. So Li Chin told you before, just to segue into the erbium-166, Li Chin discussed before how the anisotropy changes over the series. So the question is, as you go from the terbium here, which has this minimum at theta equals 0, to the erbium, which has a minimum, albeit more kind of a shallow minimum here, but an absolute minimum at around 90 Kelvin, how does that change things? All right, so let's skip over this for now. So for the erbium-166, we looked at this with neutron diffraction using HB1A at Haifer. So if we look over at the left panel here, so the top panel shows you susceptibility data taken by Tyler Slade at Ames. You see two transitions. The first transition at high temperature here corresponds to the nail transition. I'm going to call it the nail transition, and then the transition down here at lower temperature, which is first order like, which is about at 92 Kelvin. I'm going to call that the spiral transition. So what's going on? So if we look at the middle panel here, you see above the nail transition, all you see is the 002 diffraction peak here. This just corresponds to structural peak. As you cool down, you go through TN, you start seeing these incommensurate Bragg peaks appear, and these satellite Bragg peaks are actually, their position is temperature dependent. So the anti-ferromagnetic propagation vector that they correspond to is temperature dependent, and it seems to grow and then decrease as you go towards the T-spiral transition. And then when you get to below this T-spiral transition, you get the ferrimagnetic order, and the magnetic satellites disappeared, but you get magnetic intensity now on top of some of the structural Bragg peaks. So this is shown in the bottom panel here. This bottom panel is actually from data taken for 10L, so not 00L. But you can clearly see you get these satellite peaks here. So that's the green intensity growing with decreasing temperature. They suddenly disappear. And at the same time, this 100, the structural Bragg peak, is no real change. Above T-spiral, below T-spiral, you get this sudden jump in intensity. And so in addition to these main features, we also observed some fine structure in the diffraction pattern, which I'll just mention for now. You can find some more details in this archive post. But basically, these satellite magnetic Bragg peaks actually appear to be what we're calling split. So they actually don't correspond to just, say, a single Gaussian line shape. They're actually the superposition of either two or three Gaussians, and number of Gaussians changes with temperature. And that's plotted on the right here, where we show the center of each component plotted versus temperature. You can see up at high temperature, we need 3 Gaussians to describe the peak. And as we go to low temperature, you need 2 Gaussians. And actually the splittings between the two satellites becomes narrower and then widens again with temperature, but you never see the third peak reappear. The other feature we've been looking into is that if you look at the diffraction pattern here in the middle, you see the primary satellites, but then you also see peaks corresponding about to 2 tau and 3 tau. And for magnetic diffraction, you may expect seeing a 3 tau peak if you're getting a squaring up of the antiferromagnetic structure, but the 2 tau peak is more anomalous. And right now we're broadly associating the appearance of these multiple harmonics, and then also the splitting here with some kind of this subtle distortion to the magnetic structure. So the magnetic structure, it turns out we can model it as being in this, what we're calling a triple spiral order. So this is the structure between T-spiral and TN. So it's quite similar to the double spiral that's found for the yttrium manganese 6, tin 6. But in our case, of course, we have a magnetic erbium ion, and this also participates. So this bottom graph here, the numbers basically correspond to the layers on the top here going up, right? So you have manganese 1, manganese 2, erbium 3, manganese 4, manganese 5. So between bilayer manganese, you get this small splitting delta. And then between the manganese bilayers, you get this overall splitting of, or you get this overall turn angle of phi. It's this angle phi here that corresponds to the antiferromagnetic propagation vector. And then the erbium ions, they bisect this angle phi minus delta, but point against the bisector. So they point in the opposite direction. And this is similar to a structure that was seen for gallium doped thulium manganese 6, tin 6. So we looked at this in more detail with mean field theory. For this, we transferred some of the parameters over from the terbium 166 study we did, and then we also had some input from some erbium 166 inelastic neutron scattering data. Basically, we were able to prove based on the coupling parameter we found that that it's consistent with the erbium-166 having a ferrimagnetic ground state. If we overplot here, so we have here the calculated angles phi and delta as a function of temperature using the Hamiltonian I showed you before within the mean field approximation. We lay over what we found from the antiferromagnetic propagation vector. We get very good agreement between the two. And then we were also able to show that driving this spin reorientation with increasing temperature is increasing thermal fluctuations of the erbium moment. So the fluctuations increase, the ordered erbium moment decreases, and eventually you get this spin reorientation. You get this transition from the ferrimagnetic state into the spiral state. Okay. All right. So this next graph here, let's see, we're looking at some magnetization data taken at Ames. We're comparing that to the same data using our model parameters from our calculation. Again, in the ferrimagnetic state, you see this sharp step, which corresponds to what we call a FOMP, first order magnetization process, where you're going from ferrimagnetic in the AB plane, if you look over the phase diagram here, to ferrimagnetic in the C direction. And then as you warm up into this triple spiral phase, this FOMP basically disappears. You get more smooth linear type behavior before plateauing. And then, so this phase diagram on the right here is the same one Joanna showed before. Rob predicted this based on his mean field theory. So interestingly, as you apply a field, you get these various non-collinear, non-coplanar states, which may lead to some interesting topological consequences by picking up this non-zero Berry curvature. Another interesting feature that's brought out is, up here before you get into the forced ferromagnetic phase at high temperature, you actually get into this region where the erbium moment is effectively quenched due to the Zeeman energy of the high field. Okay, so I wasn't sure how much time I had, so I thought I'd put this at the end. So I'll just go through this quickly, even though this is probably one of the harder ones to explain.
Because I think you already 5 minutes over.
Yeah, all right. Well, we can stop for questions then, that's fine. But if you want to talk about this later, we can. So let me just put this up as a summary, and thank you for your time.
So the next talk is Jinha Chu from University of Washington, and he'll be speaking about giant coercivity and large anomalous Hall effect of kagome compensated ferrimagnet chromium doped terbium manganese 6 tin 6. Jinha, I can see your slides. Probably want to switch. Yeah. Yep, that looks good.
Okay, can you hear me well?
Yep, you're all set.
Okay, very good. All right, so thanks, Rob, and the organizer for inviting me to this wonderful workshop, learning a lot already. And yeah, and then it's a great pleasure to present our work here. So what I'm going to tell you here is that if you started to put chromiums into this terbium manganese tin 6, then you'll see something quite interesting. You'll actually turn this into a compensated ferrimagnets, where the magnetization is being the net magnetization being continuously suppressed and then eventually almost vanishes. But in the same time, you still see a rather strong anomalous Hall effect associated with these materials. Okay, so let me first thank the people who actually did this work. So this work is really driven by my students at postdoc Jonathan Desvetano and Elliot Rosenberg, and also with a lot of other students and postdocs within my group. So these two really forms a wonderful teams, and then exploring and venturing into all sorts of 166 compounds. And then for this particular work, it's most driven by Jonathan. So we also get a lot of theoretical support from Yongbing and Li Qing in other 166 projects, and then probably we'll get more from them on this particular project as well. And then some of the measurements are done in the high field national lab with the technical support from David Graff. And we also benefit a lot from discussion with Igor on the physics of these materials. And these research cannot be done without the funding support from these agencies. Okay, so as I said, we have venturing into the 1,6 compounds about maybe 2 years ago, and then so there's a couple of interesting results, which a lot of them you have already heard in the previous talks. For example, like the uniaxial ferromagnetism terbium vanadium 16.6, and we also see this pseudo gap behavior associated with the charge density wave fluctuations above the actual transition temperature from the magnetotransfer measurements in scandium vanadium 16.6. But here I'm going to just really focusing on this chromium substituted terbium manganese 16.6. But I'll be happy to chat with you about the results of the other projects maybe after the talk. Okay, so let's quickly review what's going on with the terbium manganese 16.6, and then so that we have an idea of what would happen with the chromium substitution. So this has already been discussed multiple times, but let me just remind you that you have this manganese moment that is ordered ferromagnetically within the plane, and then the terbium is coupled anti-ferromagnetic with the manganese layers. So this terbium kind of effectively mediated a ferromagnetic exchange between the manganese layers. So the overall manganese are ferromagnets coupled through the layers, but the terbium is anti-aligned with the manganese. Now the terbium has much stronger fluctuations and order at much have the full saturation, full ordering at much lower temperature. So this is really highlighted by this beautiful work by Namel and Igor in this preprint. So what's going to happen is that at high temperature, when you have manganese moments dominate, then you have the in-plane manganese easy plane anisotropy. So therefore, the overall system has a in-plane anisotropy, but as you get into lower temperature, then the terbium moments becomes more dominant, then you have this strong uniaxial anisotropy from the terbium, and then therefore the magnetization flips around this 300 kelvins, and then you have this spin reorientation transition. So what happens if you replace manganese with chromium? So in extreme case, when you fully substitute manganese with chromium, what you get is a much reduced temperature. So here I'm citing a paper that was published almost 30 years ago. They studied this terbium chromium 6, germanium 6. So it's not exactly Tin 6, but it's probably close enough to have an idea what's going on. So what you have is the critical temperature is reduced to 10.3 Kelvin. So it's getting close to the around 4 kelvins of the non-magnetic vanadium, terbium vanadium 16.6. So therefore, the interaction of this magnetic ordinate is really dominated by terbium. And what I found from the neutron scattering is that the chromium moment size is about 0.48. So therefore, compared to the 2.5 Bohr magneton of the manganese in terbium manganese 16.6, the total moment is much reduced. So if you just slightly substitute the chromium, what you get is that you're going to reduce the moments in the average moments in the chromiums and manganese layer. So for example, in this work that was also done quite a while ago, they studied this, they used neutron to study this chromium substituted terbium manganese 16.6 with 2 dopings. And then what they found is that the terbium moment doesn't change much. No, it's still around 8.5 to 9, but the average moments of the chromium manganese is much reduced. And then the spin reorientation temperature and the critical temperature of the ferromagnetism also being reduced. So the interesting question is that in the pairing compounds, you have totally 6 manganese with 2.5 Bohr magneton per manganese. So you total have around 14 to 15 Bohr magnetons. And then, so that is larger than the terbium moment. So when you measure the net magnetization, it is the manganese moments that is dominating the total magnetization, and the terbium moment is anti-aligned with the net magnetization. But as you reduce the average moments in the chromium and manganese layer, at some point it will become comparable to the terbium. And then that's when the net magnetization vanishes. And then it will be interesting to see what kind of physical behavior would you obtain. So this is exactly what we did. So we have grown a series of chromium dope terbium manganese 16.6 all the way from 0 to the doping range of 0.5. So almost half of the manganese is substituted by the chromium. So this is also beyond the point where we expected to have this reversal of the magnetization. So here I'm showing you the base temperature magnetization versus field plot. So in the parent compound, you have this nice hysteresis loop, and then the saturated magnetization, the value corresponding to what you will expect from 6 manganese and 1 terbium. And as you increase X, you can see the saturated magnetization being progressively decreased, and then eventually almost vanishes around 0.43, and then turning up again at 0.49. So if you actually obtain this magnetization and then plot it as a function of X, and then treating the magnetization that is above this compensation doping as the negative magnetization, then you can do a linear fit. And then what you get is that you're reducing about 1.8 Bohr magnetone when you're replacing 1 manganese with 1 chromium. So when you extrapolate all the way to 1, you get about, I think, 0.7 Bohr magnetone for the terbium chromium 16.6. So it's not far off from what people have found in the terbium chromium 6 germanium 6. Okay, so the immediate consequence of reducing this net magnetization, you can see, is the increase of coercive field. So you can see that here in the pairing compounds, the coercive field. Okay, maybe let's look at this. The coercive field is maybe of the order of 1 and 2 Tesla, but it quickly increases as the magnetization vanishes. So here I'm plotting the saturated magnetization at the base temperature as a function of doping, and then you can see that you keep decreasing and getting to 0 and then coming back again. And then the coercive field almost diverge at the point where your magnetization vanishes. So this is expected since the energy gain by moving this domain wall is coming from the magnetizations times the magnetic field. And if magnetization vanishes, then you will expect the critical field or the coercive field to overcome this domain wall pinning will also go with 1/m. So we plot this coercive field times magnetization as a function of doping, and then you can see there's a lot of variation, but more or less, it's not increasing by a lot as a function of doping or disorder. And this red data point is not really reliable, since this few data point is really beyond our 14 Tesla magnet to extract the coercive field. Okay, so this is the coercive field. Let's look at the temperature dependence of the magnetic behavior of this system. So, okay, so just recall what is being measured in the terbium manganese 16.6. So if you measure, for example, a C-axis magnetization, then, if you're measuring the magnetization with field parallel to the C-axis, so in-plane field, then you will get a large response below the ferromagnetic transition temperature, but a sudden decrease at the spin orientation temperature. And then for the field along the C-axis, you have the opposite effect, because now you have the opposite anisotropy. So if you measure the magnetization in plane of this chromium dope compound, then you get what you expected, right? So you do see this onset of the in-plane magnetizations below the ferromagnetic transition temperature, and then a sudden decrease at the spin orientation temperature. And then the overall magnetization decrease as you increase X. So based on this, you can create a phase diagram where the ferromagnetic transition temperature and the spin orientation temperature are being progressively suppressed by X. So there seems to be, everything seems to be what is expected. However, if you look at the out-of-plane magnetization, something quite interesting happened. So for the lower doping, you do see something similar to the parent compound with an increase of magnetization. But you also see a decrease of magnetization as you go in to lower temperature. And then for the higher doping, this decrease become more and more prominent. And then you even see this negative magnetization in the negative magnetization or negative magnetic response at the lower temperature. So namely, you apply a small field and then you cool down, and then the magnetization decided to go to the opposite direction to what you initially apply. So a very strong diamagnetic response. So how to understand this? So obviously this negative magnetization is coming from these unusual temperature dependence or unusual asymmetry of temperature dependence between the terbium and manganese moments, where the manganese or chromium average moments are saturated at a much higher temperature scale compared to the terbium moments. So if you look at these compounds and then doing an M versus H curve for different temperature, then what's really happening is that at high temperature, you have the usual self-ferromagnetic response. But at some temperature where the magnetization vanishes, you have the total compensation. So this is exactly the point when this terbium moments grows and then become comparable to the manganese magnetization, manganese or chromium average magnetization. So therefore magnetization vanishes. But at the time when this magnetization grows again, you have a much larger coercive field compared to the higher temperature where you have similar magnetization. So when you're applying a small field, you polarize the magnet so that the total moment is parallel to the manganese moments. But at a time when the terbium moments surpass the manganese moments, you're trapped in this state, and then you cannot overcome the coercive field. So therefore, you get a negative magnetization. So obviously you won't see that in M versus H, because with a larger field, you'll be able to fully polarize back so that the magnetization is along the net magnetization direction. However, this allows us to create some very interesting states. For example, in this higher doping or in this slightly lower doping where you have even larger coercive field, so that at low temperature, this coercive field is beyond 14 Tesla. You can cool it at a small field, either positive field and negative field, and then you can see this magnetization reversal at this intermediate temperature. And then you apply you apply a large field in low temperature, and then you can see that the state is frozen in this opposite magnetization state, right? For example, this is cool in a negative 0.1 Tesla, you get a positive magnetization, and then even if you apply field, it's frozen into that state, and you cannot flip the magnetization, or vice versa. And we don't really know what's going on with this very small, strong soft paramagnetic behavior at low temperature at this point. Okay, now I'm going to switch gear and talk about anomalous Hall effect in this system. So let me just quickly review what we know about the anomalous Hall effect in terbium manganese 16.6. So let's first look at this very famous Nature paper on this terbium manganese 16.6. And I guess a lot of us are being attracted by this compound because of this work. So they have found that if they, there's a large intrinsic anomalous Hall effect in this system, which they can obtain by doing this power law scaling fitting of the rho anomalous Hall versus rho XX squared. And here, by extracting the constant and then the quadratic coefficient, then you can separate the intrinsic and skew scattering part, and then obtain an intrinsic anomalous Hall about 121 Siemens per centimeter inverse, and then which corresponding to 0.14 E squared over H. And then they argue that this is due to this this work by Jiaxing and Hassan's group, which they argues that this is due to this gapped spin polarized Dirac fermion. Now, a later work by Nermel and Igor, they have found something different. So they found out that this anomalous Hall actually cannot fit very well just by this extrinsic and intrinsic. So that will correspond to this black curve. The model will correspond to a black curve. And then they have to include an additional term, which is a term that has a spin fluctuations. And then with that term, they can fit this whole anomalous hole conductivity and versus conductivity very well. And then they found out that they get a anomalous hole, intrinsic anomalous hole conductivity around 140. So not very far from the original numbers, but they also did band structure calculation and then realized that there's actually a lot of barrier curvature source everywhere in the band structure. So it's not particularly limited to that gap Dirac fermion. So what do we find in the anomalous hole? So let's first look at this temperature dependence, where we see this magnetization reversal. So this is the same kind of magnetization versus edge I showed you earlier, different temperature. And then you can see that this anomalous hole is already pretty pronounced at the high temperature. And then even when the magnetization is about to vanish, you still have rather substantial anomalous hole resistivity. But as you go to lower temperature, when the magnetization appears again, then the anomalous hole, the sign of the anomalous hole reversed. So now you have the opposite sign of the anomalous hole, and then it remains strong all the way down to low temperature, and then with the same coercive field of the magnetization. So what this is telling us is that the anomalous hole doesn't really care about the net magnetization. So the anomalous hole is actually really following the magnetizations of the manganese. So at high temperature, when the manganese moment dominate, then the field is always parallel to the manganese moments. So therefore, you have a positive sign of the anomalous hole coefficient. However, as you go to low temperature, when the magnetization reversal happens, then the manganese moment is anti-parallel to the field. So therefore, you have a negative anomalous hole coefficient. So similar things can be seen in the doping. So as a function of doping, you can also see that the anomalous hole persists even when the magnetization vanishes. So here in this yellow curve where the magnetization vanishes just because the coercive field is too large, so we cannot see the flipping of the rho xy, but if you actually feel cool, you can actually see the anomalous hole, and it remains comparable to the neighboring dopant. But what is quite interesting is that the anomalous hole resistivity actually grows when you go to higher doping. So since anomalous hole resistivity is not that transparent, or it's not that directly related to the things we care about, you can convert this to the anomalous hole conductivity and then plot it as a function of temperature. Then you see this reversal of the anomalous hole conductivity as a function of temperature for certain doping, but you also see that the magnitude of the anomalous hole conductivity doesn't really vanishes and even gets stronger when you go to higher doping. And then one thing to notice is that as you dope this compound, so terbium manganese 6, tin6 is a very good metal with a very high triple R. So you have a very wide range of conductivity at low temperature. Once you start to dope and you introduce disorder, and then the conductivity being kind of pushed to a much lower value. So if you compare this to this very famous sigma xy, sigma xx log plot, then you realize that in this high doping region, you're really confined this anomalous hole behavior really in this intrinsic regime. Now, to be more quantitative, we also fit the anomalous hole resistivity and anomalous hole conductivity with the model that Igor and Nermel developed, including this spin fluctuation term. So this C is the intrinsic term, and then I believe this D is the spin fluctuation term, and then this A is the extrinsic skew scattering term. So with this model, the data is fitted pretty well. You can either fit it with the resistivity or fit it with the conductivity. The resistivity fit a bit better, and then conductivity fitted reasonably okay. But the coefficient you extracted are more or less agree with each other. And then perhaps more importantly, if you look at the intrinsic part, it's showing very consistent results, which is as you're going from pairing compound to the dope compound, the anomalous hole, intrinsic anomalous hole conductivity is progressively increased to a much larger value. So if we look at some calculations, so for example, here I'm pointing to a work, an experimental work where Bing Hai did calculations on the doping dependence of the anomalous hole conductivity. And I think Igor's and Ramel's paper also have something similar. So because you have this Berry curvature source everywhere in this compound, so there's really nothing special about the Fermi level at the for the terbium manganese 16.6. In fact, if you hold doping, which is what we are doing with the chromium, replacing manganese with chromium and reducing the number of d electrons, then you will get a much larger anomalous hole conductivity. And then this is precisely what we have observed. Now the anomalous hole conductivity is increased by almost threefolds as we dope to 0.28. Okay, so let me just put this into a bigger picture, which is in the community of spintronics. Now people are gradually moving from this ferromagnet spintronics to anti-ferromagnet spintronics, and then also ferromagnet spintronics. So the idea is the following. So the ferromagnets, it has a spin polarizations and a magnetization. So it is easy to control and then also easy to read out. But this easy access also offers a lot of problems. For example, like you have stray field, so that when you try to make very dense memory device, then this stray field can affect the next cell. And also because this net magnetization, a lot of dynamics is much smaller. So therefore, people begin to think about the anti-ferromagnet spintronics, where things, the moments could, the switching can happen in a much faster time scale. And also there's zero stray field, so there's no interference for the neighboring memory cells. Now the problem is that here you don't have any magnetization, so it's very difficult to control. And then also you have no Zeeman splitting in the Fermi level, so and then no anomalous hole effect. So it's also very difficult to read out. So the compensated ferromagnet kind of offer a balance where you can try to create a net magnetization, zero states by just compensating two kinds of moments. In the same time, you also have large anomalous hole effects to read. And then perhaps there's ways you can kind of switch the magnetization on and out, just like what we were seeing with the temperature, and then you can control it and then reduce the magnetization to zero so that the stray field doesn't really affect the next memory cell. So in this sense, this chromium dope terbium manganese 16.6 almost fit this picture almost perfectly, where you have zero net magnetization with a very large anomalous hole effect. Okay, so in summaries, we have a lot of fun in this chromium dope terbium manganese 16.6, and then there's a wide range of interesting phenomena such as magnetization reversal and giant coercitivity, and then the enhanced anomalous hole effect. So this is really just by changing one element in this compound, and there's such a large phase space in all this 166 material. So who knows, what you will find or what we'll find by playing with other elements. Okay, so that's all. Thank you for your attention.